Something doesn't add up. Astronomers have spent decades mapping the universe, charting every star, every planet, every galaxy they can find. But there's a problem. There are entire galaxies out there, faint, barely visible collections of stars, behaving in ways that make no sense. They're called ultra-faint dwarf galaxies, and they shouldn't exist the way they do. They defy everything we know about gravity, dark matter, and galaxy formation. Some scientists even think they might hold the key to understanding what the universe is really made of. But here's the real kicker. We don't even know how many of them are out there. And the ones we found? They're breaking every rule in the book. To understand why ultra-faint dwarf galaxies are such a big deal, let's break it down. A normal galaxy, like the Milky Way, is massive. It has hundreds of billions of stars, planets, gas, dust, and dark matter all working together in a gravitational balance. Dwarf galaxies are smaller versions of that, usually just a few billion stars or less. But ultra-faint dwarfs? They take it to another level. Some of them have only a few thousand stars. That's barely a fraction of a normal galaxy's mass. Imagine taking the entire Milky Way and shrinking it down until it has fewer stars than some star clusters. That's how tiny these things are. But here's the weird part. Even though they barely have any stars, they seem to have a massive amount of dark matter. In fact, some of them are almost entirely made of dark matter, with just a tiny sprinkling of visible stars. That alone is strange enough, but it gets even weirder. Most galaxies form from collapsing clouds of gas that condense under their own gravity. They start with a lot of material, and over time, that material turns into stars, planets, and other structures. But ultra-faint dwarfs? They don't seem to follow that pattern. Many of them don't have nearly enough gas to form new stars. Some of them are so old that they haven't formed a single new star in billions of years. It's like they got frozen in time shortly after the Big Bang. And here's where things take a turn for the truly bizarre. Some ultra-faint dwarfs don't even orbit larger galaxies like they're supposed to. Instead, they drift through space, almost like ghosts, barely interacting with the rest of the universe. The discovery of ultra-faint dwarf galaxies is actually pretty recent. Until the 2000s, astronomers didn't even know they existed. They were just too dim to detect with older telescopes. But then, new surveys, like the Sloan Digital Sky Survey and later the Dark Energy Survey, started picking up strange, faint collections of stars hiding in the background of the sky. At first, they looked like random noise, but when astronomers studied them closer, they realized they weren't just stars. They were entire galaxies. And some of them were orbiting the Milky Way. But they weren't like the normal satellite galaxies we already knew about. These new galaxies were much fainter, much smaller, and much more mysterious. One of the biggest mysteries surrounding ultra-faint dwarfs is how they ended up with so much dark matter. Based on everything we know about galaxy formation, smaller galaxies should have less dark matter, not more. But ultra-faint dwarfs seem to be the opposite. Some of them have 99% or more of their total mass made up of dark matter. That means the stars we can see are just tiny specks floating in an invisible halo of something we can't detect directly. And if that's true, then ultra-faint dwarfs could be some of the best evidence we have for the existence of dark matter. Scientists have been searching for dark matter for decades, trying to figure out what it's made of, how it interacts with normal matter, and why we can't see it. But ultra-faint dwarfs might hold the answer. If we can study them closely enough, we might finally be able to figure out what dark matter actually is. Another strange thing about these galaxies is their distribution. When astronomers mapped out the locations of the ultra-faint dwarfs orbiting the Milky Way, they noticed something odd. Instead of being scattered randomly around the galaxy, they seem to be arranged in a thin, flat plane, almost like a giant cosmic disk. That doesn't make sense. Galaxies shouldn't arrange themselves like that. If they form naturally from collapsing gas clouds, they should be in a more random distribution. But they're not. This has led some scientists to propose a radical idea. What if these galaxies didn't form the way we think? What if they were actually stolen from another galaxy? There's a theory that some ultra-faint dwarfs might be remnants of ancient galaxy mergers. Billions of years ago, the Milky Way could have collided with another galaxy, stripping away smaller satellites and leaving them in strange, unexpected orbits. If that's true, then these tiny galaxies might be some of the oldest relics in the universe, leftovers from a time when the Milky Way itself was still forming. But that's not the only theory. Some astronomers think that ultra-faint dwarfs might not be galaxies at all, at least not in the way we normally think. Instead, they might be the remains of primordial dark matter structures that never fully developed into galaxies. If that's the case, then these objects could be some of the earliest building blocks of the cosmos, predating even the first normal galaxies. One of the strangest ultra-faint dwarf galaxies ever discovered is called Segue 1. It's one of the dimmest galaxies ever found, with only a few hundred stars. But despite its tiny size, it has an enormous amount of dark matter. In fact, it's one of the most dark matter-dominated objects in the known universe. If we could figure out why Segue 1 is the way it is, it might give us a huge clue about the nature of dark matter itself. Some theories suggest that ultra-faint dwarfs like Segue 1 could be made up of exotic dark matter particles that don't behave like anything we've ever seen before. If that's true, then studying them might be our best shot at finally proving what dark matter actually is. But there's a problem. These galaxies are incredibly difficult to study. They're so faint that even the most powerful telescopes struggle to detect them. And because they don't produce much light, it's nearly impossible to get detailed information about what's inside them. Scientists have to rely on indirect methods, like measuring the motions of their stars to estimate how much dark matter they contain. And even then, there's still a lot we don't know. Some ultra-faint dwarfs might be hiding in plain sight, blending in with the background of the universe. Others might be so far away that we haven't even begun to detect them. And there's always the possibility that some of them don't fit into any of our existing models at all. The mystery of ultra-faint dwarf galaxies is one of the biggest open questions in modern astronomy. Are they the missing link in our understanding of dark matter? Are they remnants of ancient cosmic collisions? Or are they something even stranger, evidence of a new kind of physics that we haven't even begun to understand? Scientists are still searching for answers, but one thing is certain: whatever the truth is, it's going to change the way we think about the universe forever. Ultra-faint dwarf galaxies are not just tiny cosmic oddities. They might be the key to unlocking some of the biggest mysteries in astrophysics. Their existence alone challenges the way we think about galaxy formation, dark matter, and even the structure of the universe itself. But to truly understand why these galaxies are so important, we need to go deeper into the strange physics that governs them, the bizarre ways they behave, and what their existence tells us about the unseen forces shaping the cosmos. One of the strangest things about ultra-faint dwarf galaxies is how incredibly stable they are. You might think that such small, fragile structures, barely holding together with just a few thousand stars, would be easily torn apart by gravitational forces. But they aren't. They seem to be held together by something incredibly powerful, something that ordinary matter alone can't explain. And that's where dark matter comes in. Dark matter is one of the biggest unsolved mysteries in physics. We can't see it, we can't touch it, and we have no idea what it's made of. But we know it's there because we can see its effects. Galaxies rotate in ways that don't make sense unless there's some unseen mass providing extra gravity. Large cosmic structures, like galaxy clusters, wouldn't be able to hold together without it. And ultra-faint dwarf galaxies? They might be the best evidence of dark matter we've ever found. Here's why. In a normal galaxy, like the Milky Way, the visible stars and gas account for only a small fraction of its total mass. The rest is dark matter, an invisible substance that doesn't interact with light but still has gravity. But in ultra-faint dwarf galaxies, the ratio is extreme. In some cases, the amount of dark matter is hundreds or even thousands of times greater than the visible stars. That means these galaxies are basically just dark matter with a handful of stars sprinkled in. This is why ultra-faint dwarfs are so stable. Even though they barely have any visible mass, their enormous halos of dark matter act like a kind of cosmic glue, holding them together against the pull of the Milky Way and other gravitational forces. And this raises a huge question: why do these galaxies have so much dark matter in the first place? Shouldn't they follow the same patterns as other small galaxies? Scientists don't have a definitive answer yet, but there are a few leading theories. One idea is that ultra-faint dwarfs formed in the very early universe, back when conditions were completely different from what they are today. In this scenario, dark matter clumped together first, forming dense halos before ordinary matter had a chance to collapse into stars. If this is true, then these galaxies could be some of the first structures that ever formed in the cosmos. They could be fossils from a time when the universe was still in its infancy, containing clues about how dark matter shaped everything that came after. Another theory suggests that these galaxies might not have formed in the usual way at all. Instead of slowly building up from gas and dust, they could have been the remnants of larger galaxies that were stripped down by gravitational interactions. If a normal dwarf galaxy passed too close to the Milky Way, for example, its stars and gas could have been pulled away, leaving behind only the densest core, an ultra-faint dwarf that's mostly made of dark matter. This would explain why some ultra-faint dwarfs have such strange orbits, moving in ways that don't fit with traditional models of galaxy formation. But there's an even weirder possibility. What if ultra-faint dwarfs are actually signs of new physics? What if the way we think about dark matter is completely wrong? Some scientists have proposed that dark matter might not be a simple, invisible particle, but something much more complex. There are theories suggesting that dark matter could interact with itself in ways we don't understand yet, forming invisible structures, creating pressure forces, or even having its own kind of dark chemistry. If that's true, then ultra-faint dwarf galaxies might be telling us something groundbreaking about the hidden side of the universe. One of the biggest mysteries surrounding ultra-faint dwarfs is why we've found so few of them. Based on our best simulations of how the universe evolved, there should be hundreds or even thousands of these galaxies orbiting the Milky Way. But we've only detected a few dozen. This is known as the missing satellites problem, and it's one of the biggest challenges in modern astrophysics. There are a few possible explanations. One is that ultra-faint dwarfs are just incredibly hard to find. Since they barely produce any light, they could be hiding in plain sight, blending into the background noise of the universe. Some of them might be so faint that even our most powerful telescopes can't detect them yet. If that's the case, then future telescopes, like the Vera C. Rubin Observatory, might reveal hundreds of new ultra-faint dwarfs we've never seen before. Another possibility is that something is actively destroying these galaxies. If ultra-faint dwarfs are mostly made of dark matter, they might be especially vulnerable to interactions with larger galaxies. The Milky Way's gravity could be pulling them apart, stripping away their dark matter halos until they dissolve completely. If this is happening, then we might only be seeing the ones that are lucky enough to have survived. But the strangest explanation of all is that our entire understanding of dark matter could be wrong. Some physicists have suggested that the reason we don't see as many ultra-faint dwarfs as expected is because dark matter doesn't behave the way we think it does. Instead of being a simple, invisible mass that just adds extra gravity, dark matter might have complex interactions that prevent it from forming certain structures. If that's the case, then ultra-faint dwarfs might be the key to proving that dark matter is far more than we ever imagined. The study of ultra-faint dwarf galaxies is still in its early stages, but every new discovery brings us closer to solving some of the biggest questions in physics. These tiny, ghost-like galaxies could be the missing link between what we see in the universe and the invisible forces that shape it. They could hold the answer to why galaxies form the way they do, how dark matter influences cosmic structures, and even whether our fundamental theories of gravity need to be rewritten. And the biggest question of all? If ultra-faint dwarf galaxies are this strange, what else is out there that we haven't found yet? The universe is full of mysteries, and every time we think we understand it, something new comes along that changes everything. The deeper we look into the cosmos, the more bizarre ultra-faint dwarf galaxies become. They don't just challenge our understanding of dark matter, they also raise serious questions about how galaxies form, evolve, and interact with their surroundings. But perhaps the strangest thing about them is how they seem to defy the very physics that governs ordinary galaxies. Take their star formation, for example. In most galaxies, stars form when clouds of gas collapse under gravity, igniting nuclear fusion in their cores. But in ultra-faint dwarfs, star formation is almost non-existent. Many of these galaxies appear to have stopped producing new stars billions of years ago, long before the Milky Way had even fully formed. This suggests that something prevented them from gathering enough gas to sustain star formation. One possible explanation is that these galaxies were stripped of their gas early in their history. If they formed in the chaotic early universe, they might have been bombarded by intense radiation from young, massive stars or even blasted by the energetic winds of the first supermassive black holes. This radiation could have heated up their gas to the point where it was no longer able to collapse into stars. If this happened, then ultra-faint dwarfs might be fossils from a time when the universe was still violently shaping itself. Another possibility is that ultra-faint dwarfs simply never had much gas to begin with. If these galaxies formed in small pockets of dark matter, far away from larger structures, they might have never been able to accumulate enough material for sustained star formation. Instead, they could be leftover fragments, pieces of the early universe that never grew into full-fledged galaxies. But the most mind-bending theory of all is that ultra-faint dwarf galaxies might be showing us a completely new way for galaxies to exist. What if some galaxies don't need ordinary matter at all? What if dark matter can form structures that we've never even considered before? Some physicists have speculated that dark matter might be able to interact with itself in complex ways, creating invisible galaxies that don't follow the usual rules of physics. If that's true, then ultra-faint dwarfs could be the first hints of an entirely new form of cosmic structure, one that we're only just beginning to understand. And then there's the question of their orbits. Ultra-faint dwarf galaxies don't move the way we expect them to. While most small galaxies tend to follow smooth, predictable paths around larger galaxies, ultra-faint dwarfs seem to have highly unusual orbits. Some of them move in strange, looping patterns, while others appear to be falling toward the Milky Way at high speeds. This has led some scientists to speculate that they might not be ordinary satellite galaxies at all. One radical idea is that these galaxies were not originally part of the Milky Way's system. Instead, they could have been captured from another cosmic structure, perhaps even an entirely different galaxy cluster. If this is the case, then ultra-faint dwarfs might not just be fossils of the early universe, but also relics from ancient galactic collisions. These galaxies could be the last survivors of violent interactions that happened billions of years ago, drifting through space like cosmic debris. Another possibility is that ultra-faint dwarfs are being actively influenced by dark matter itself. Some alternative theories of dark matter suggest that it could create invisible streams or filaments that guide the movement of galaxies. If ultra-faint dwarfs are trapped in one of these dark matter structures, then their strange orbits might be evidence of forces we can't directly detect. But perhaps the biggest mystery of all is what ultra-faint dwarfs could tell us about the fate of our own galaxy. If these tiny, ghost-like galaxies are the remnants of larger systems that were torn apart, could the same thing eventually happen to the Milky Way? Could we one day see our own galaxy stripped down to a faint shadow of what it once was, drifting through space like an ultra-faint dwarf? Some astronomers believe that studying these galaxies could give us a glimpse into the far future of the universe. If ultra-faint dwarfs are what happens when galaxies lose their mass and energy over billions of years, then they could be showing us a slow-motion preview of what might happen to all galaxies given enough time. The universe is constantly evolving, and nothing stays the same forever. And that raises an even bigger question: how many of these galaxies are still out there, waiting to be discovered? If we've only found a fraction of the ultra-faint dwarfs that should exist, what else are we missing? Could there be entire hidden structures in the universe that we simply haven't been able to see yet? As technology advances and new telescopes come online, we're likely to find even more of these strange galaxies. The Vera C. Rubin Observatory, set to begin operations soon, is expected to uncover dozens, if not hundreds, of new ultra-faint dwarfs. And each new discovery could bring us closer to understanding not just how galaxies form, but also the fundamental nature of dark matter itself. But the real question isn't just what we'll find, it's what it will mean. If ultra-faint dwarf galaxies truly are dominated by dark matter, they could provide the best testing ground we've ever had for dark matter theories. They could help us determine whether dark matter is made of simple, weakly interacting particles, or if it has complex properties that we've never even imagined. And if we find that ultra-faint dwarfs behave in ways that can't be explained by dark matter at all, that might mean we're on the verge of a scientific revolution, one that could completely rewrite our understanding of gravity, physics, and the structure of the universe itself. For now, ultra-faint dwarf galaxies remain one of the strangest, most enigmatic mysteries of space. They are whispers from the early universe, ghostly remnants of a time long past, and possibly the key to solving one of the biggest scientific puzzles of all time. The more we study them, the more questions we have. And as we continue to push the limits of our knowledge, one thing is certain: the universe is far stranger than we ever imagined. Ultra-faint dwarf galaxies are like time capsules, holding secrets from a period of cosmic history that we can barely begin to understand. They exist on the edge of what our current telescopes can detect, their dim light barely reaching us across the vast distances of space. Yet, despite their faintness, they might hold the answers to some of the biggest mysteries in astrophysics. One of the strangest aspects of ultra-faint dwarf galaxies is how they seem to challenge our fundamental assumptions about dark matter. In standard models, dark matter is thought to be smoothly distributed throughout a galaxy, providing a gravitational framework that allows normal matter to settle and form stars. But in ultra-faint dwarfs, the expected balance between dark matter and normal matter seems completely off. In many of these galaxies, the ratio of dark matter to normal matter is so extreme that it almost seems as if these galaxies shouldn't exist at all. Some ultra-faint dwarfs contain hundreds, or even thousands, of times more dark matter than visible matter. This has led to one of the most controversial debates in modern astrophysics. Are we missing something fundamental about how dark matter works? One possibility is that dark matter in these galaxies behaves differently than in larger galaxies. Some theories suggest that dark matter might not be completely inert. It could interact with itself in ways we don't fully understand. If this is true, then ultra-faint dwarfs could be the best place to test these ideas. By studying how these galaxies move, astronomers might be able to determine whether dark matter has subtle self-interactions that haven't been detected in other environments. But there's also an even stranger possibility. What if ultra-faint dwarf galaxies are showing us that dark matter doesn't exist at all? Some alternative theories of gravity, such as modified Newtonian dynamics, (MOND), propose that what we perceive as dark matter might actually be the result of gravity behaving differently on cosmic scales. In this framework, ultra-faint dwarfs could be behaving oddly because gravity itself is acting in ways we don't yet understand. If true, this would mean that our entire understanding of the universe's structure needs to be rethought. It would mean that dark matter, a concept that has guided cosmology for decades, might not be real. Instead, the force of gravity itself might need to be rewritten to account for these puzzling observations. This debate isn't just theoretical. Observations of ultra-faint dwarf galaxies have already produced some of the strongest challenges to our current dark matter models. For instance, some ultra-faint dwarfs appear to lack dark matter entirely, something that should be impossible if dark matter is the glue that holds galaxies together. How can a galaxy exist without dark matter, while others are almost entirely made of it? One leading explanation is that these galaxies might have formed under very different conditions than typical galaxies. If an ultra-faint dwarf was once part of a larger system, it might have been stripped of its dark matter through interactions with other galaxies. This could explain why some of them appear to be almost entirely devoid of dark matter while others are packed with it. But if this explanation is correct, it raises another unsettling question: how common are these interactions? Could it be that many small galaxies lose their dark matter over time, changing their structure in ways we don't yet understand? If so, it could mean that dark matter isn't as stable as we once thought. It might be something that galaxies can gain or lose over time, depending on their cosmic environment. This could have massive implications for our understanding of how galaxies evolve. If dark matter is more dynamic than we thought, then our models of galaxy formation might need to be completely revised. It could mean that entire populations of galaxies have vanished without a trace, their dark matter stripped away until they simply faded into the cosmic background. And this brings us to another mind-bending idea. What if ultra-faint dwarfs are just the remnants of much larger galaxies that were torn apart by unseen forces? Some astronomers have speculated that these tiny galaxies might be all that remains of ancient galactic structures that were destroyed billions of years ago. If so, they could be like fossils, evidence of galactic cannibalism on a scale we've never imagined. In fact, there's growing evidence that the Milky Way itself has devoured multiple smaller galaxies over the course of its history. Some ultra-faint dwarf galaxies might be the last survivors of these events, still lingering in the outskirts of our galaxy, slowly being pulled apart by gravitational forces. If this is the case, then ultra-faint dwarfs could provide direct evidence of how galaxies grow over time, not just through the gradual accumulation of matter, but through violent, chaotic interactions that leave behind scattered remnants. They could be the missing pieces of a cosmic puzzle, showing us that the universe isn't just a place of slow, steady evolution, but also one of destruction and rebirth. But there's still another layer to this mystery. How did these galaxies get so faint in the first place? If they were once part of larger systems, then what caused them to lose so much of their mass and light? One possibility is that they experienced a process known as quenching. This happens when a galaxy is stripped of the materials needed for star formation, causing it to stop producing new stars and slowly fade over time. In the case of ultra-faint dwarfs, this quenching process might have happened billions of years ago, leaving them as relics of an earlier era. But how does quenching happen? One major culprit could be the environment these galaxies exist in. If an ultra-faint dwarf passes too close to a massive galaxy like the Milky Way, it could experience something called ram pressure stripping. This is when a galaxy moves through a dense region of intergalactic gas, which literally blows away its own gas, leaving it unable to form new stars. Another possibility is that these galaxies were affected by powerful bursts of radiation in the early universe. If they formed at a time when the first stars and black holes were producing intense energy, their gas could have been heated up and blown away before they had a chance to fully develop. But here's where things get even weirder. Some ultra-faint dwarfs show signs that they've remained unchanged for almost the entire history of the universe. They contain some of the oldest known stars, suggesting that they formed very early on and then simply stopped evolving. This makes them invaluable to astronomers. If these galaxies really have remained frozen in time, they could be some of the purest examples of the first galaxies ever to exist. They might hold clues about what the universe was like before larger galaxies like the Milky Way even formed. This is why studying them is so important. They're not just strange, isolated objects. They could be the keys to unlocking the history of the cosmos itself. They could reveal what the universe was like in its infancy, how the first galaxies formed, and whether our current understanding of dark matter and gravity is even correct. And yet, despite everything we've learned, we're still barely scratching the surface. Every new ultra-faint dwarf that's discovered brings more questions than answers. Some seem to be completely dominated by dark matter, while others seem to lack it entirely. Some appear to be remnants of ancient galaxies, while others might be entirely new structures we've never seen before. The mystery is far from solved. In fact, it might be one of the biggest mysteries in modern astrophysics. And as our technology improves and our ability to observe the faintest objects in the universe gets better, we may finally start to unravel the secrets of these ghostly galaxies. But one thing is certain, the universe is far stranger, more complex, and more mysterious than we ever imagined. And ultra-faint dwarf galaxies are just one small piece of a much bigger puzzle, one that we're only beginning to understand. Ultra-faint dwarf galaxies are a paradox in every sense. Their very existence forces us to reconsider long-held ideas about how galaxies form, how they interact with their environments, and even the fundamental nature of dark matter itself. These galaxies defy our expectations in ways that seem almost impossible. Some of them contain hardly any stars at all, just a small scattering of ancient ones that have been burning for billions of years. Others appear to be almost entirely composed of dark matter, as if they are nothing more than ghostly frameworks of invisible mass, with only the faintest hints of light to mark their presence in the cosmos. And then there are the ultra-faint dwarfs that seem to have formed under conditions that make no sense based on our current models. Some are so isolated that they should never have been able to form in the first place, yet there they are, drifting in the cosmic void, stubbornly refusing to disappear. Others orbit the Milky Way in strange, seemingly unnatural arrangements, as if they were placed there by some unknown force rather than evolving naturally through gravitational interactions. One of the most baffling aspects of ultra-faint dwarf galaxies is their apparent immunity to the forces that should have torn them apart. Conventional wisdom tells us that small galaxies are fragile. They should be easily disrupted by the gravitational influence of larger galaxies, or by the tides of intergalactic space. And yet, some ultra-faint dwarfs have remained largely unchanged for billions of years, surviving against all odds in environments that should have destroyed them long ago. This is particularly strange when you consider that the Milky Way has been actively consuming smaller galaxies for billions of years. We see evidence of this all around us. Streams of stars stretching across the night sky, the remnants of once proud galaxies that were torn apart by our own galaxy's gravitational pull. So why are some ultra-faint dwarfs still intact while others have been shredded into nothingness? One possibility is that they formed in regions of space where conditions were different than anything we've seen before. If these galaxies were born in deep voids, where there was very little normal matter to begin with, they might have developed in ways that are completely different from other galaxies. Instead of being dominated by star formation, they might have been dominated by dark matter from the very beginning, creating structures that are fundamentally unlike anything we've encountered before. If this is the case, then ultra-faint dwarf galaxies could be offering us a glimpse into a hidden side of the universe, one where normal matter plays a much smaller role than we ever imagined. This could mean that dark matter isn't just a background player in the cosmic story, but something far more important, perhaps even the primary driver of galaxy formation in some cases. This idea has enormous implications for our understanding of the cosmos. If ultra-faint dwarfs can form and persist in ways that don't fit within our current models, it could mean that the large, bright galaxies we see today are actually the exceptions, not the rule. It could mean that the universe is filled with far more dark matter-dominated structures than we ever thought possible, hiding in the depths of space, beyond the reach of our telescopes. And if that's true, then the implications are staggering. It could mean that our understanding of how galaxies form is incomplete. It could mean that our theories about dark matter are missing something fundamental. It could mean that the universe is structured in ways that we have yet to even comprehend. But perhaps the most intriguing possibility of all is that ultra-faint dwarf galaxies might be the missing link between the earliest galaxies and the ones we see today. If these tiny galaxies really are fossils from the early universe, then they might be holding on to secrets that have been lost in time, clues about what the cosmos was like before galaxies like the Milky Way even existed. Some astronomers have suggested that ultra-faint dwarfs could be the remnants of the very first galaxies ever to form. If this is the case, then they might contain stars that are among the oldest in the universe, stars that formed just a few 100 million years after the Big Bang, before the first galaxies had even fully assembled. If we can study these stars in detail, we might be able to learn what the universe was like in its infancy, how the first structures formed, and whether our current theories about the early universe are correct. But studying these galaxies is incredibly difficult. Because they are so faint, they are nearly impossible to detect with most telescopes. It has only been in recent years that advances in astronomical technology have allowed us to identify them at all. Even now, we have only scratched the surface. There could be countless more ultra-faint dwarfs lurking in the darkness, waiting to be discovered. And that's perhaps the most exciting part of this mystery. We are still at the very beginning. Every new ultra-faint dwarf galaxy that we discover brings us one step closer to understanding the hidden structure of the universe. Every new observation challenges our assumptions, forcing us to rethink what we thought we knew. The more we study them, the more it becomes clear that these galaxies are not just anomalies. They are crucial pieces of the cosmic puzzle. They might hold the answers to some of the biggest questions in physics. What is dark matter? How do galaxies form? What was the universe like in its earliest moments? As our technology continues to improve, we will be able to study these galaxies in greater detail than ever before. Future telescopes, like the Vera C. Rubin Observatory and the next generation of space telescopes, will allow us to detect even fainter galaxies, pushing the boundaries of our knowledge even further. And maybe, just maybe, hidden in the depths of one of these ultra-faint dwarf galaxies, we will find the answer to one of the greatest mysteries in astrophysics. Ultra-faint dwarf galaxies may seem small and insignificant compared to massive galaxies like the Milky Way, but their implications are anything but minor. In fact, these galaxies might hold the key to unlocking some of the greatest secrets of the universe. One of the most puzzling aspects of these galaxies is their extreme dark matter content. Unlike traditional galaxies, which have a healthy balance of visible matter and dark matter, ultra-faint dwarfs appear to be almost entirely composed of dark matter, with only a tiny fraction of their mass being made up of stars and gas. This is strange because, according to conventional galaxy formation models, dark matter alone shouldn't be enough to create a galaxy. It should need at least some normal matter to form stars and keep the structure stable. So how do these galaxies exist? One theory suggests that ultra-faint dwarfs are the remnants of the first galaxies that formed in the early universe. If this is true, they could be some of the oldest surviving structures in existence, preserving the original conditions of the cosmos before larger galaxies came into being. This would make them invaluable time capsules, allowing us to peer into the distant past and study how the first galaxies formed. If these galaxies are truly fossils from the early universe, they could contain some of the oldest stars ever discovered, stars that date back to the first few 100 million years after the Big Bang. These ancient stars could provide vital clues about the early universe's chemistry, revealing what the cosmos was like before heavier elements were forged in the hearts of dying stars. If we can study these ultra-faint dwarfs in enough detail, we might be able to learn more about the very first generation of stars, which astronomers believe were much larger and more massive than today's stars, burning incredibly hot and bright before exploding as supernovae. But even beyond their connection to the early universe, ultra-faint dwarf galaxies are deeply intertwined with the mystery of dark matter. Their unusual structure suggests that dark matter plays an even more dominant role in galaxy formation than we previously thought. Most galaxies contain a mix of dark matter and normal matter, but ultra-faint dwarfs seem to break this pattern. In some cases, they have so little normal matter that they appear to be held together almost entirely by dark matter's gravitational pull. This has led some scientists to propose that these galaxies might be some of the purest dark matter structures in existence. If we can study these galaxies closely, they might help us uncover the true nature of dark matter. So far, dark matter remains one of the biggest mysteries in modern physics. We know it exists because of the way it affects galaxies and large-scale cosmic structures, but we have never directly observed it. It doesn't emit light, doesn't interact with normal matter in any way that we can currently detect, and only makes itself known through gravity. Yet, according to current models, dark matter makes up about 85% of the total mass of the universe. Ultra-faint dwarf galaxies might offer us a rare opportunity to study dark matter in its purest form. Because these galaxies have so little normal matter, they provide a cleaner environment for testing dark matter theories. Scientists can analyze how stars move within these galaxies to determine the distribution of dark matter, which could give us crucial insights into what dark matter actually is. Is it made up of weakly interacting particles, as many scientists believe? Or could it be something even more exotic? Perhaps a new type of fundamental particle that we have yet to discover? There are also theories suggesting that ultra-faint dwarf galaxies could be connected to modified gravity theories, alternative explanations that challenge the idea of dark matter entirely. Some physicists have proposed that our understanding of gravity itself might be incomplete, and that ultra-faint dwarfs could be the key to proving or disproving these alternative models. If these galaxies behave differently than expected based on their dark matter content, it could indicate that our current understanding of gravity needs to be revised. Another baffling mystery surrounding these galaxies is their strange orbital behavior. Many of the ultra-faint dwarf galaxies that orbit the Milky Way do not follow the paths that we would expect based on traditional models. Instead of being randomly distributed around our galaxy, many of them seem to align in vast, thin planes, an arrangement that is difficult to explain using standard galaxy formation theories. Some astronomers have even suggested that this peculiar alignment could indicate the presence of unseen cosmic structures, or that these galaxies were placed in their orbits by unknown forces at work in the early universe. This mystery deepens when we consider that some ultra-faint dwarfs appear to have been stripped of their gas and stars, leaving behind little more than dark matter skeletons. The cause of this stripping is not entirely understood. It could be the result of interactions with the Milky Way's gravitational field, or it could be evidence of an even more mysterious process, perhaps interactions with an unknown form of matter or an undiscovered cosmic force. One of the most extreme examples of this is the galaxy Segue 1, which is often considered the faintest known galaxy. It contains only a handful of stars but appears to be dominated by an enormous amount of dark matter. If Segue 1 truly represents an ultra-faint dwarf that has been stripped down to its core, it could provide valuable insights into how galaxies evolve under extreme conditions. But there's another possibility that is even more mind-bending. What if some of these ultra-faint dwarfs aren't actually galaxies at all? Some researchers have speculated that these objects could be something entirely different, perhaps dark matter, halos, that never fully developed into galaxies, or even remnants of failed galaxy formation attempts from the early universe. If this is the case, then studying them could reveal entirely new physics, challenging everything we thought we knew about how structures in the universe form and evolve. As astronomers continue to discover more ultra-faint dwarf galaxies, the mystery only deepens. The more we look, the more it seems that these galaxies are not rare anomalies but rather common features of the universe that have remained hidden from view until now. With new observational tools like the Vera-C, Rubin Observatory and upcoming space missions, we are on the verge of a new era in our understanding of these enigmatic structures. If we can unlock the secrets of these galaxies, we might finally answer some of the most profound questions in astrophysics. What is dark matter? How do galaxies form? What was the universe like in its earliest moments? And perhaps most intriguingly, what else is out there, lurking in the darkness, waiting to be discovered? The mystery of ultra-faint dwarf galaxies is far from solved, but one thing is certain: they are forcing us to rethink the universe in ways we never expected. Every new discovery brings us closer to understanding their true nature, and with each passing year, the pieces of the puzzle are slowly coming together. The next decade of research could change everything we thought we knew about the cosmos. And as we continue to search the vastness of space, who knows what else we might find? Perhaps the next great cosmic revelation is just waiting to be uncovered, hidden in the depths of one of these ghostly galaxies, challenging us to see the universe in an entirely new way. The mystery of ultra-faint dwarf galaxies is like a puzzle with missing pieces. Every time we think we've found a piece that fits, new observations raise more questions. One of the strangest aspects of these galaxies is their unusual chemical composition. Unlike larger galaxies, which contain a mix of old and young stars, ultra-faint dwarfs seem to be frozen in time. The stars they contain are some of the oldest in the universe, and many of these galaxies show little to no evidence of recent star formation. This suggests that something stopped them from growing billions of years ago. But what could have halted their development? One possibility is that these galaxies formed early in the universe's history and then ran out of gas, preventing them from forming new stars. This could have happened if powerful cosmic events, like supernova explosions or interactions with larger galaxies, stripped away their star-forming material. Another theory suggests that cosmic reionization, the period in the early universe when the first stars and galaxies emitted high-energy radiation that ionized hydrogen gas, heated the gas within these small galaxies, making it impossible for them to form stars. If this theory is correct, ultra-faint dwarfs could be direct relics of this ancient era, offering us a glimpse into a time when the first galaxies were taking shape. Some ultra-faint dwarfs also seem to lack the heavier elements that are common in other galaxies. These elements, such as carbon, oxygen, and iron, are produced in the cores of massive stars and spread throughout the universe by supernova explosions. The fact that ultra-faint dwarfs have so few of these elements suggests that they have experienced very little star formation over their lifetimes. This supports the idea that they are ancient remnants from the early universe, largely unchanged since their formation. But if ultra-faint dwarfs are truly fossils from the early universe, then why do some of them behave so strangely? One of the most bizarre discoveries about these galaxies is that some of them appear to contain more dark matter than we thought possible. In some cases, the amount of dark matter inferred from the motion of stars is hundreds, or even thousands of times greater than the mass of the stars themselves. This extreme dark matter dominance challenges our understanding of galaxy formation and suggests that these galaxies could be some of the best natural laboratories for studying dark matter. If dark matter is a type of undiscovered particle, as many scientists believe, then ultra-faint dwarfs could help us figure out how it interacts with normal matter. By studying the way stars move within these galaxies, researchers can test different dark matter models. Some models suggest that dark matter particles should occasionally collide and annihilate each other, producing faint signals that could be detected by telescopes. If ultra-faint dwarfs contain high concentrations of dark matter, they might be the best places to search for these signals. But there's another possibility that is even more unsettling. What if ultra-faint dwarfs don't behave the way we expect because our entire understanding of gravity is incomplete? Some alternative theories of gravity, such as modified Newtonian dynamics, (MOND), propose that dark matter might not exist at all, that instead, the laws of gravity change on cosmic scales in ways we don't yet understand. If ultra-faint dwarfs show unexpected gravitational behavior, they could provide evidence for these alternative theories. One of the strangest observations supporting this idea comes from the way some of these galaxies orbit the Milky Way. Instead of being randomly distributed, many of them seem to align in vast, thin planes that defy conventional models of galaxy formation. Some astronomers believe this unusual alignment could be a sign that our understanding of gravity needs to be revised. Others argue that it could be the result of interactions with dark matter structures that we cannot directly observe. Adding to the mystery, some ultra-faint dwarf galaxies appear to be disappearing. In a few cases, astronomers have detected galaxies that seem to be dissolving as they orbit the Milky Way, their stars slowly being stripped away until nothing remains. What causes this process? It could be gravitational interactions with the Milky Way itself, but some researchers speculate that an unknown cosmic force might be at work, something that is affecting these galaxies in ways we do not yet understand. The discovery of new ultra-faint dwarfs is still ongoing. With every new telescope and survey, astronomers are finding more of these elusive galaxies, each one adding another layer to the mystery. Some of the latest discoveries suggest that ultra-faint dwarfs might be even more common than we previously thought, hidden in the vast darkness of space, waiting to be found. If we can uncover their secrets, we might finally understand how galaxies formed in the early universe, what dark matter really is, and whether our understanding of gravity itself needs to change. The mystery of ultra-faint dwarf galaxies is far from solved, but one thing is clear: they are forcing us to rethink everything we thought we knew about the cosmos. Ultra-faint dwarf galaxies continue to challenge our understanding of how galaxies form and evolve. While their extreme dark matter dominance is one of their most baffling characteristics, another major puzzle is their origin. Where did these galaxies come from? Are they remnants of the first galaxies in the universe, or were they once larger galaxies that were stripped down to their current form? One hypothesis is that ultra-faint dwarfs are fossil galaxies that formed more than 13 billion years ago, during the universe's infancy. If this is true, they could be among the oldest structures still in existence, containing clues about the very first stars that ever formed. These galaxies might have been the first to accumulate dark matter, creating dense halos that attracted gas and triggered early star formation. However, at some point, something halted their growth, leaving them frozen in time. The cosmic reionization event that occurred around 12.8 billion years ago could be a key factor in explaining why these galaxies stopped growing. During this period, the universe was flooded with high-energy radiation from the first stars and black holes. This intense radiation could have heated and ionized the gas in ultra-faint dwarfs, making it impossible for them to form new stars. Unlike larger galaxies, which had enough mass to hold onto their gas, these tiny galaxies may have lost their ability to form stars entirely. If this theory is correct, ultra-faint dwarfs could be the closest thing we have to direct evidence of the first galaxies ever to form. But there is another theory, one that suggests that these galaxies were not always so small. Some astronomers believe that ultra-faint dwarfs were once much larger galaxies that were stripped down over billions of years by interactions with the Milky Way and other massive galaxies. If a small galaxy passed too close to a much larger one, powerful gravitational forces could have torn it apart, stripping away stars and gas while leaving behind only the dense dark matter core. This process, known as tidal stripping, could explain why some ultra-faint dwarfs appear to be dissolving as they orbit the Milky Way. If this theory is correct, then ultra-faint dwarfs are not just relics of the early universe. They are survivors of violent cosmic interactions. But how can we tell the difference between a fossil galaxy and a stripped-down remnant of a larger one? The answer might lie in their chemical composition. Fossil galaxies should have extremely low levels of heavier elements, since they stopped forming stars billions of years ago. Stripped galaxies, on the other hand, should have at least some traces of more recent star formation before they were torn apart. Recent observations of ultra-faint dwarfs suggest that both scenarios might be true. Some appear to be ancient relics, while others show signs of past interactions with larger galaxies. This means that ultra-faint dwarfs could be a diverse group of galaxies with different origins, adding yet another layer of complexity to their mystery. One of the most intriguing aspects of these galaxies is their relationship with dark matter. Ultra-faint dwarfs are some of the most dark matter-dominated galaxies ever discovered, with stars that appear to be orbiting within vast halos of invisible matter. This makes them ideal laboratories for studying the nature of dark matter. Some dark matter theories suggest that it should occasionally interact with itself, leading to faint but detectable signals. Ultra-faint dwarfs, with their high dark matter-to-star ratios, are considered prime locations to search for these signals. Scientists have used gamma-ray telescopes to scan these galaxies for signs of dark matter annihilation, but so far, no definitive signals have been detected. This lack of evidence is puzzling, as some dark matter models predict that ultra-faint dwarfs should be among the best places to detect these interactions. This has led some researchers to question whether our understanding of dark matter is incomplete. If dark matter is not interacting in the ways we expect, could it mean that we need to rethink its properties? Or could it be that ultra-faint dwarfs contain an unusual form of dark matter that behaves differently from what we predicted? Some alternative theories suggest that dark matter might not be a particle at all but instead a fundamental modification of gravity. If this is the case, ultra-faint dwarfs could hold the key to a completely new understanding of the universe. Adding to the enigma, some ultra-faint dwarfs appear to be defying standard models of galaxy formation. Many of these galaxies are not randomly distributed around the Milky Way but instead align in vast, thin planes. This plane of satellites phenomenon is difficult to explain using traditional models, which predict that dwarf galaxies should be scattered more randomly. The fact that so many ultra-faint dwarfs seem to align in this way suggests that something is shaping their orbits, something that current models do not fully account for. One possibility is that these galaxies are tracing hidden structures of dark matter, forming along invisible filaments that stretch across the cosmos. If this is true, then ultra-faint dwarfs could be revealing the cosmic web in ways we have never seen before. Another possibility is that these galaxies formed in the same large-scale event billions of years ago, such as a past collision between the Milky Way and another massive galaxy. As we continue to study these galaxies, new discoveries are constantly reshaping our understanding. One of the most exciting developments is the potential discovery of even fainter galaxies that push the limits of detection. Some researchers believe that there could be thousands of ultra-faint dwarfs lurking in the darkness, waiting to be found. If we can detect these even fainter galaxies, they could provide crucial insights into the nature of dark matter, the early universe, and the true structure of our galaxy. With the development of more powerful telescopes, such as the Vera C. Rubin Observatory, we are on the brink of uncovering even more secrets about these mysterious objects. Ultra-faint dwarfs are not just small, dim galaxies. They are cosmic fossils, dark matter laboratories, and possible clues to new physics. They challenge our understanding of how galaxies form, how dark matter behaves, and even how gravity works on the largest scales. As we continue to explore the universe, these enigmatic galaxies will undoubtedly play a crucial role in shaping our understanding of the cosmos. But despite all we have learned, the mystery of ultra-faint dwarfs is far from solved. Every new discovery seems to raise more questions than answers. Why do some of these galaxies seem to be dissolving while others remain intact? Why are they so overwhelmingly dominated by dark matter? What is causing them to align in strange formations around the Milky Way? Could they be revealing hidden forces or structures that we have yet to detect? The search for answers continues, and as technology advances, we may one day unlock the secrets of these strange galaxies. Until then, ultra-faint dwarfs remain one of the greatest unsolved mysteries of space, a reminder that the universe is far more complex and mysterious than we ever imagined. The deeper we look into the universe, the stranger ultra-faint dwarf galaxies become. Despite their minuscule size and faint luminosity, these galaxies refuse to be ignored. They challenge our understanding of dark matter, galaxy formation, and even the fundamental laws of physics. And the more we study them, the more it seems like we've barely scratched the surface of their mysteries. One of the biggest ongoing debates is how many of these galaxies actually exist. The number of ultra-faint dwarfs we've detected is surprisingly low, too low, in fact, when compared to what standard models of galaxy formation predict. According to our best simulations, there should be hundreds, possibly thousands, of ultra-faint dwarf galaxies orbiting the Milky Way. And yet, we've only found a small fraction of that number. This discrepancy is known as the missing satellites problem. If our models of dark matter and galaxy formation are correct, there should be far more ultra-faint dwarfs out there than we've found. So where are they? Are they hiding in the depths of space, too faint to detect with current telescopes? Or is there something fundamentally wrong with our understanding of how galaxies form? One possible explanation is that many ultra-faint dwarfs are simply too dim for us to see with existing telescopes. These galaxies contain so few stars that their light barely reaches us, making them nearly invisible against the backdrop of space. Some astronomers believe that with more powerful telescopes, we will eventually find many more ultra-faint dwarfs, helping to close the gap between predictions and observations. Another possibility is that our models of galaxy formation are incomplete. Maybe something happened in the early universe that prevented many of these galaxies from forming or surviving. Cosmic reionization, the event that flooded the universe with ionizing radiation, might have played a larger role than we realize. If the radiation was intense enough, it could have completely shut down star formation in many small galaxies, leaving behind only dark matter halos with no visible stars. If these dark galaxies exist, they would be nearly impossible to detect, even with the most powerful telescopes. But what if the problem isn't with galaxy formation, but with dark matter itself? Our current models assume that dark matter consists of cold, slow-moving particles that clump together to form halos around galaxies. But if dark matter behaves differently, if it is warm, or interacts with itself in unexpected ways, it could prevent the formation of the small galaxies we expect to see. Some physicists even suggest that dark matter might not be a particle at all, but a modification of gravity. If this is true, then the missing satellites problem might not be a problem at all. It could simply be evidence that our entire understanding of the universe is flawed. This is what makes ultra-faint dwarfs so important. These galaxies are pushing the limits of what we think we know about dark matter, galaxy formation, and the structure of the universe. Every time we discover a new ultra-faint dwarf, we get one step closer to understanding these fundamental mysteries. But at the same time, each new discovery raises more questions than answers. Some of the most recent discoveries have only deepened the mystery. Astronomers have found ultra-faint dwarf galaxies that appear to contain almost no dark matter at all, something that should be impossible under our current understanding. If dark matter is the invisible glue that holds galaxies together, then how can these galaxies exist without it? Are they being held together by something else? Or do these discoveries suggest that dark matter behaves in ways we don't yet understand? Adding to the strangeness, some ultra-faint dwarfs appear to be moving in coordinated, organized patterns around the Milky Way. Instead of being randomly distributed, many of these galaxies align in vast, thin planes. This arrangement is difficult to explain with current models, which predict that dwarf galaxies should be scattered more chaotically. Some scientists believe that this alignment could be evidence of an undiscovered force or structure shaping their orbits. Others suggest that these galaxies were formed in the same ancient event, possibly a massive collision that disrupted the Milky Way billions of years ago. Then there's the question of their star populations. Unlike larger galaxies, ultra-faint dwarfs contain extremely old stars, some of the oldest in the universe. These stars have incredibly low levels of heavy elements, suggesting that they formed in the very early universe, before multiple generations of star formation enriched galaxies with heavier elements. If ultra-faint dwarfs truly are relics of the first galaxies, then studying their stars could give us a direct glimpse into what the universe was like more than 13 billion years ago. But here's where things get even stranger. Some ultra-faint dwarfs show signs of unusual chemical compositions that don't match anything we expect. Their stars contain odd ratios of elements, suggesting that they experienced only a few, highly unusual supernova explosions in their history. This could mean that ultra-faint dwarfs formed in environments unlike anything we've ever seen. It could also mean that they were shaped by rare, violent events, possibly even collisions with dark matter itself. And what about the ones that are disappearing? Some ultra-faint dwarf galaxies appear to be slowly dissolving as they orbit the Milky Way, losing stars and gas over time. In some cases, their stars are stretching out into long, thin streams, a clear sign that these galaxies are being torn apart by gravitational forces. But why are some dissolving while others remain intact? Are we witnessing the final moments of galaxies that have existed for billions of years? Or are these galaxies just the remnants of a much larger cosmic event we don't yet understand? As technology advances, we are on the verge of discovering even more about these strange galaxies. The upcoming Vera C. Rubin Observatory is expected to find many new ultra-faint dwarfs, potentially solving the missing satellites problem, or making it even more confusing. Meanwhile, the James Webb Space Telescope could peer deep into these galaxies, revealing their true age, structure, and chemical composition in unprecedented detail. Ultra-faint dwarfs might not be the most visually impressive galaxies in the universe, but they are among the most scientifically significant. They are challenging our understanding of dark matter, rewriting our models of galaxy formation, and revealing new clues about the earliest days of the universe. They may even hold the key to discovering new physics, something that could change our entire understanding of reality itself. And yet, for all we've learned, the mystery is far from over. Every answer leads to more questions. Why do some ultra-faint dwarfs contain almost no dark matter? Why do they align in strange patterns around the Milky Way? Could they be revealing hidden forces or structures in the universe? Or are they simply the survivors of a chaotic, violent past? The search for answers continues, and with every new discovery, we move one step closer to solving one of the greatest mysteries of space. But until then, ultra-faint dwarf galaxies remain a cosmic enigma, a reminder that the universe is full of surprises, waiting to be uncovered. The more we study ultra-faint dwarf galaxies, the more we realize how much they challenge our understanding of the cosmos. These galaxies are not just minor footnotes in the grand story of the universe. They could be the missing pieces of a much larger puzzle, one that might force us to rethink the very fabric of space, time, and matter itself. And the deeper we dig, the stranger things get. Consider the idea that some ultra-faint dwarf galaxies might not even be real galaxies in the way we typically define them. Normally, galaxies are held together by a delicate balance of gravity, dark matter, and the motion of their stars. But some of these ultra-faint dwarfs appear to lack enough mass to explain how they remain intact. They should have been ripped apart by the gravitational pull of the Milky Way long ago. And yet they persist, as if some invisible force is keeping them together. One theory is that these galaxies are stabilized by a form of dark matter that behaves in a way we don't yet understand. This could mean that dark matter isn't just a simple, uniform substance but something far more complex, perhaps with its own interactions and forces that we haven't yet detected. Some scientists even propose that ultra-faint dwarf galaxies could be made up almost entirely of exotic forms of dark matter, with only a tiny number of visible stars marking their presence. Another bizarre possibility is that some of these galaxies could be relics from a time before galaxies, as we know them, even existed. They might be surviving fragments of primordial structures that formed shortly after the Big Bang. If this is the case, then these galaxies are living fossils, frozen snapshots of the universe's infancy, preserving conditions that existed billions of years ago. Studying them could give us insights into how the first structures in the cosmos emerged from the chaotic soup of the early universe. But then there's the even stranger idea. What if some ultra-faint dwarf galaxies aren't entirely natural? What if they show signs of something artificial, something that doesn't fit within the expected patterns of galactic evolution? While this might sound like science fiction, some researchers have considered the possibility that the unusual properties of certain ultra-faint dwarfs could be the result of advanced civilizations manipulating their environments on a galactic scale. If an ancient civilization had the ability to harness dark matter or alter the structures of galaxies, could the ultra-faint dwarfs we see today be the remnants of their experiments? Of course, this is highly speculative. But the mere fact that ultra-faint dwarf galaxies raise these kinds of questions shows just how little we truly understand about them. These galaxies don't just challenge our models of physics and cosmology. They push the limits of our imagination, forcing us to consider possibilities we never thought possible. And the mysteries keep stacking up. Some ultra-faint dwarf galaxies have been found to have unexpectedly high levels of certain heavy elements, something that shouldn't be possible given their size and history. This suggests that at some point in their past, these galaxies experienced intense and unusual bursts of star formation, possibly triggered by interactions with dark matter or by unknown cosmic events. Other ultra-faint dwarfs seem to be missing key ingredients that every other known galaxy possesses. Some appear to lack hydrogen gas, which is essential for forming new stars. Without this gas, these galaxies should be dead, unable to create new generations of stars. But strangely, some still show faint signs of ongoing star formation, hinting at a mysterious source of fuel that we haven't yet identified. Then there's the question of their survival. The Milky Way's gravity is constantly pulling on its smaller satellite galaxies, stretching and distorting them over time. Many ultra-faint dwarf galaxies appear to be on the verge of being torn apart, with long, faint trails of stars stretching behind them. But some seem to be incredibly resilient, maintaining their structure despite the immense gravitational forces acting upon them. What makes these galaxies so resistant to destruction? Do they contain an unknown stabilizing force? Or are they protected by hidden dark matter structures that we can't yet detect? As if all this wasn't strange enough, some ultra-faint dwarfs seem to be moving in ways that completely defy expectations. Instead of following the predicted orbits around the Milky Way, some appear to be on paths that suggest they were thrown into our galaxy from somewhere else, possibly even from another galaxy entirely. Could these galaxies be refugees from intergalactic space, flung into our neighborhood by ancient cosmic collisions? And what about the ones we haven't found yet? Many astronomers believe that we've only detected a tiny fraction of the ultra-faint dwarf galaxies that exist. If there are hundreds or even thousands more lurking in the darkness, what secrets could they hold? Could some of them contain entirely new forms of matter? Could they reveal hidden interactions between dark matter and normal matter that we've never seen before? One of the most exciting upcoming projects in this field is the Segue Observatory, which is set to revolutionize our ability to detect faint objects in the night sky. With its powerful survey capabilities, it could uncover a vast number of new ultra-faint dwarf galaxies, shedding light on their distribution, properties, and potential connection to dark matter. But there's also a chance that it could reveal something completely unexpected, something that forces us to rewrite our understanding of the cosmos entirely. At the same time, telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope will allow us to peer deeper into these galaxies than ever before. By analyzing their stars and chemical compositions in unprecedented detail, we may finally unlock the secrets of their origins. But even as we move forward, one thing is certain: ultra-faint dwarf galaxies are not just small, insignificant objects. They are cosmic anomalies, holding answers to some of the biggest questions in astrophysics. They challenge our understanding of dark matter, galaxy formation, and the very structure of the universe. And perhaps most intriguingly, they remind us that the universe is still full of surprises. No matter how much we think we know, there will always be mysteries lurking in the darkness, waiting for us to uncover them. Ultra-faint dwarf galaxies are not just a minor quirk of the cosmos. They are windows into an unknown side of reality, where the rules we think we understand begin to break down. Every new discovery about them deepens the mystery, revealing unexpected details that challenge what we thought was possible. But as strange as these galaxies are, they might be the key to unlocking some of the biggest unanswered questions in astrophysics. One of the strangest aspects of ultra-faint dwarf galaxies is how little visible matter they contain. Compared to normal galaxies, they have almost no stars, no gas, and no dust. In fact, many of them seem to be made almost entirely of dark matter, with only a handful of stars sprinkled throughout. This defies everything we know about galaxy formation. Normally, galaxies form when clouds of gas collapse under their own gravity, triggering the birth of new stars. But these dwarfs seem to have formed without enough gas to create stars in the first place. How did they form? What forces allowed them to exist at all? One idea is that ultra-faint dwarfs are some of the oldest structures in the universe, fragments left over from the earliest days after the Big Bang. If this is true, then these galaxies could be the closest thing we have to time capsules, preserving the conditions of the early universe in a way that nothing else does. Some scientists believe that by studying these galaxies, we might be able to see the influence of the very first dark matter structures, which acted as gravitational seeds that eventually pulled in normal matter and formed galaxies. But what if these galaxies didn't form naturally at all? What if their strange properties hint at something more exotic, something we've never even considered? Some researchers have proposed that ultra-faint dwarf galaxies could be the result of dark matter behaving in an unexpected way. One possibility is that dark matter isn't just a simple, passive material but something much more dynamic, something that can form structures of its own. If dark matter can clump together in ways we don't yet understand, then some of these galaxies might not be galaxies in the traditional sense at all. They could be dark matter hubs, gravitationally bound by invisible forces we have yet to detect. This brings us to an even more mind-bending idea. What if some of these galaxies are actually artificial? While this sounds like science fiction, there's a growing discussion in astrophysics about the possibility that highly advanced civilizations, if they exist, might manipulate dark matter for their own purposes. If an ancient civilization had the ability to control or modify dark matter, it could theoretically create structures that look like ultra-faint dwarf galaxies to us. Could these galaxies be the remnants of experiments? Could they be the cosmic ruins of a civilization that existed billions of years ago? While we have no evidence for this yet, the fact that these galaxies behave so strangely means that we have to keep an open mind. Another perplexing mystery is why some ultra-faint dwarf galaxies seem to be missing key elements that are found in almost every other galaxy. Many of them lack hydrogen gas, which is essential for forming new stars. Without hydrogen, these galaxies should have stopped forming stars billions of years ago. But strangely, some of them still show weak signs of ongoing star formation. Where is this fuel coming from? Is there a hidden source of hydrogen that we haven't detected? Or is there some unknown process at work, allowing new stars to form in an environment where they shouldn't be able to exist? Then there's the question of their movement. The Milky Way's gravity should be pulling these dwarf galaxies into predictable orbits. But some of them seem to be moving in ways that completely defy expectations. Instead of following the expected paths, some ultra-faint dwarf galaxies appear to be on bizarre, erratic trajectories. This suggests that they may not have formed in the Milky Way at all. Some astronomers think these galaxies could be intergalactic wanderers, ejected from their original locations by violent cosmic events. If true, then these galaxies could have traveled unimaginable distances, carrying with them secrets from entirely different regions of the universe. Some of the most exciting research in this field is focused on uncovering more ultra-faint dwarf galaxies. Many scientists believe that we have only found a small fraction of them and that there could be hundreds, or even thousands, more hidden in the darkness. The Vera C. Rubin Observatory, set to begin its survey of the night sky soon, could reveal a massive population of these galaxies that we've never seen before. If we find enough of them, we might be able to piece together a clearer picture of how they form, how they survive, and what they might be telling us about the nature of dark matter. At the same time, advanced telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope will allow us to study these galaxies in greater detail than ever before. By analyzing their chemical compositions, star formations, and movements, we may finally begin to unlock their secrets. But as history has shown, every time we think we've figured something out, the universe surprises us. It's entirely possible that ultra-faint dwarf galaxies will lead us to discoveries that go beyond anything we can currently imagine. One of the biggest open questions is whether these galaxies could contain entirely new forms of matter. Some theories suggest that certain ultra-faint dwarf galaxies might be the best places to look for evidence of exotic particles, such as axions, hypothetical particles that could help explain the nature of dark matter. If we find unusual signals coming from these galaxies, it could be the first concrete evidence of new physics beyond the standard model. And then there's the question of survival. Many ultra-faint dwarf galaxies are on the verge of being torn apart by the gravitational pull of the Milky Way. Some already show long, faint trails of stars stretching behind them, indicating that they are slowly being pulled apart. But others remain remarkably intact, resisting destruction in ways that we don't fully understand. Do they contain hidden dark matter structures that protect them? Or is there some unknown force at play, holding them together against all odds? All of this points to one undeniable fact. Ultra-faint dwarf galaxies are some of the strangest, most intriguing objects in the universe. They challenge our understanding of galaxy formation, dark matter, and the very nature of reality itself. They force us to question whether we truly understand how the cosmos works. And perhaps most importantly, they remind us that the universe is still full of surprises. As our technology advances, we will continue to uncover more about these mysterious galaxies. But for now, they remain one of the biggest cosmic puzzles, waiting for us to find the missing pieces. And who knows? The next discovery could change everything we thought we knew about the universe. The deeper we dive into the mystery of ultra-faint dwarf galaxies, the more we realize that they are not just oddities of the cosmos. They could hold the key to some of the biggest unsolved questions in astrophysics. These galaxies seem to defy our understanding of how the universe works, and every attempt to explain them only leads to more questions. Could they be relics from a time before galaxies as we know them even existed? Are they made of an exotic form of dark matter that behaves in ways we have never observed before? Or is there something even more bizarre at play, something we haven't even begun to consider? One of the strangest things about ultra-faint dwarf galaxies is that they appear to contain far more dark matter than normal galaxies. In most galaxies, dark matter makes up about 85% of the total mass, while the remaining 15% is visible matter, stars, gas, and dust. But in ultra-faint dwarfs, dark matter seems to make up as much as 99.99% of the total mass. That means these galaxies are almost entirely invisible, with only a few scattered stars giving away their presence. This extreme imbalance makes them some of the best places to study dark matter directly. If we can figure out how dark matter behaves in these galaxies, we might be able to learn what it actually is, whether it's made of unknown particles, some new form of gravity, or something even stranger. But the problem is, dark matter still refuses to reveal its secrets. Despite decades of research, we have never directly detected a dark matter particle. All we know is that it interacts with gravity but seems to be completely invisible to light and other forms of radiation. The fact that ultra-faint dwarf galaxies contain so much dark matter should make them ideal laboratories for testing dark matter theories, yet they continue to defy our expectations. Some scientists believe that the dark matter in these galaxies might be clumping together in ways we don't understand. Others suggest that ultra-faint dwarf galaxies might contain a different kind of dark matter, something more complex than the simple, collisionless particles we usually assume dark matter to be. If that's the case, then studying these galaxies could completely rewrite what we know about the universe's invisible mass. Another big mystery is why some ultra-faint dwarf galaxies seem to have formed stars long after they should have stopped. In most cases, these galaxies contain almost no gas, which means they shouldn't be able to form new stars at all. But a few of them have shown signs of recent star formation, which raises the question, where are they getting the material to make new stars? One possibility is that they are stealing gas from their surroundings, but in the vast emptiness of space, this seems unlikely. Another theory is that the dark matter itself is somehow influencing star formation in ways we don't yet understand. If dark matter can interact with normal matter in more ways than just gravity, it might be helping these galaxies form new stars under conditions that should be impossible. There's also the question of their distribution. Ultra-faint dwarf galaxies are often found orbiting larger galaxies like the Milky Way, but they don't follow the patterns we would expect. Some of them appear to be arranged in strange, disk-like formations rather than being randomly distributed, which has led some scientists to question whether they are natural at all. Could they be the remnants of ancient cosmic structures that collapsed long ago? Or could they have been shaped by unknown forces, perhaps even artificial ones? While this might sound far-fetched, the unusual properties of these galaxies make it difficult to rule anything out entirely. One of the biggest puzzles surrounding ultra-faint dwarf galaxies is their survival. Many of them are being torn apart by the gravitational pull of the Milky Way, slowly dissolving into streams of stars that stretch across the sky. But some of them seem to be holding together despite all odds. What's keeping them intact? Some researchers suspect that these galaxies might contain unusually dense concentrations of dark matter, which could act like an invisible glue holding them together. Others think that some unknown force might be at play, keeping these galaxies from being completely destroyed. If we can figure out why some ultra-faint dwarf galaxies survive while others are ripped apart, we might uncover new clues about how galaxies evolve over time. The next few decades will be crucial for solving the mystery of ultra-faint dwarf galaxies. New telescopes and surveys will allow us to find more of them, study their properties in greater detail, and test new theories about their origins. The Vera C. Rubin Observatory, for example, is expected to discover hundreds of new ultra-faint dwarf galaxies, providing a much larger sample to study. At the same time, the James Webb Space Telescope will allow us to analyze the chemical compositions of these galaxies, revealing details about their history and formation. But even with these advanced tools, there's no guarantee that we will find simple answers. The more we learn about ultra-faint dwarf galaxies, the more it seems like they are trying to tell us something profound about the nature of the universe, something we haven't yet figured out how to hear. Could these galaxies be proof that our understanding of gravity is incomplete? Some researchers have proposed that ultra-faint dwarf galaxies could be evidence for alternative theories of gravity, such as modified Newtonian dynamics, MOND, or other exotic ideas that attempt to explain the effects we currently attribute to dark matter. If these theories turn out to be correct, then ultra-faint dwarfs could force us to rethink everything we thought we knew about the fundamental laws of physics. Or could these galaxies be the best place to search for entirely new forms of matter? Some theories suggest that the dark matter in these galaxies could be interacting with itself in ways we haven't yet detected, creating new forces or even new particles that we have never observed before. If that's the case, then studying these galaxies could lead to discoveries that go far beyond astrophysics, potentially unlocking new physics that could change our understanding of the universe itself. One thing is certain: ultra-faint dwarf galaxies are among the strangest and most fascinating objects in the cosmos. They challenge our assumptions, defy our models, and hint at mysteries we have yet to solve. Whether they are the remnants of the first galaxies, evidence of new physics, or something even stranger, they remind us that the universe is still full of surprises. And as we continue to explore and study these ghostly galaxies, one thing is clear: we are only just beginning to uncover their secrets. Ultra-faint dwarf galaxies stand at the frontier of our cosmic ignorance, almost as if they exist to remind us how little we truly understand about the universe. Every new observation seems to contradict our expectations, and rather than solving the puzzle, each discovery adds more missing pieces. Could they be relics from a primordial era, older than the universe's first great galaxies? Or could they be whispers of something even more mysterious, an unknown force shaping the cosmos in ways we have yet to comprehend? One of the most baffling aspects of ultra-faint dwarf galaxies is how they manage to remain gravitationally bound despite their extremely low stellar content. With so few visible stars, these galaxies should be fragile, easily disrupted by the gravitational tides of the larger galaxies they orbit. Yet some of them remain intact, seemingly held together by an unseen force. This force is almost certainly dark matter, but the way it behaves in these galaxies raises troubling questions. Standard models of dark matter predict a smooth distribution of mass, yet ultra-faint dwarf galaxies often show signs of unexpected clumping, as if the dark matter within them is denser in certain areas than in others. This raises the possibility that dark matter might not be as simple as we think. It could be self-interacting, forming hidden structures that influence the evolution of these galaxies. Some researchers have even speculated that ultra-faint dwarf galaxies could contain dark matter that behaves in exotic ways, perhaps forming stable dark matter cores, rather than being smoothly distributed throughout space. This could explain why some of these galaxies appear resistant to tidal forces, while others are slowly being torn apart. If dark matter is not a single type of particle but instead a complex family of different particles, then ultra-faint dwarfs could be our best chance at detecting these variations. Adding to the mystery, astronomers have discovered that some ultra-faint dwarf galaxies contain unexpectedly high amounts of heavy elements, materials that should only be present in galaxies that have undergone significant star formation over long periods. This raises an intriguing question. If ultra-faint dwarf galaxies formed in the early universe and remain mostly unchanged, then where did these heavy elements come from? One possibility is that these galaxies might have experienced sudden bursts of star formation in their past, triggered by interactions with other galaxies or the accretion of intergalactic gas. Another possibility is that these galaxies might have merged with even smaller proto-galaxies, absorbing their stars and enriching their chemical composition. Yet, the mystery deepens when we consider the possibility that ultra-faint dwarf galaxies might not be entirely natural formations at all. Their unusual distributions, sometimes appearing in thin, disk-like planes around larger galaxies, have led some researchers to speculate that they might be the remnants of past galactic collisions or even artificial structures created by unknown cosmic forces. While this might seem like science fiction, the fact remains that their existence challenges many of our standard models of galaxy formation. Another perplexing aspect of ultra-faint dwarf galaxies is their relationship with dark energy, the mysterious force responsible for the accelerated expansion of the universe. If dark matter is the invisible glue holding galaxies together, then dark energy is the opposite force, pushing everything apart. But ultra-faint dwarf galaxies seem to exist in a delicate balance between these two forces. Some astronomers have proposed that studying their motions and distributions could provide new insights into how dark energy interacts with matter on cosmic scales. The upcoming generation of astronomical instruments promises to shed new light on these enigmatic galaxies. The Vera C. Rubin Observatory will conduct deep sky surveys, potentially uncovering hundreds or even thousands of new ultra-faint dwarfs, giving us a much larger sample to study. The James Webb Space Telescope, with its ability to peer into the infrared spectrum, might allow us to analyze the chemical compositions of these galaxies with unprecedented detail, revealing secrets about their formation and evolution. Meanwhile, advancements in dark matter research, whether through particle accelerators, underground detectors, or indirect astrophysical observations, could help us determine whether the strange properties of ultra-faint dwarf galaxies are linked to the fundamental nature of dark matter itself. But even with these powerful tools, one thing is clear: ultra-faint dwarf galaxies are not going to give up their secrets easily. They exist at the very limits of detectability, often appearing as nothing more than a handful of stars scattered across vast distances. Their dimness and isolation make them incredibly difficult to study, and every piece of data we collect only adds to the mystery. They defy our models, challenge our assumptions, and hint at physics we do not yet understand. Could these galaxies be remnants of the first structures to form in the universe? Could they be the missing link between normal galaxies and the vast cosmic web of dark matter that shapes the universe? Or could they be something even stranger, evidence of unknown forces or even hints of cosmic phenomena beyond our current understanding? One thing is certain: ultra-faint dwarf galaxies are among the strangest objects in the cosmos, and they hold secrets that could revolutionize our understanding of the universe. As we continue to search for answers, we must remain open to possibilities we have not yet imagined, because in the end, the greatest mysteries of the universe are often hidden in the places we least expect. Ultra-faint dwarf galaxies force us to rethink not just the structure of the cosmos but the very laws that govern it. Their existence alone challenges some of the most well-established theories in astrophysics, pushing the boundaries of what we thought was possible. Scientists have spent years trying to piece together the puzzle of these galaxies, and yet, every answer leads to even more questions. Could they be remnants of the earliest galaxies ever formed? Could they be ghostly imprints of failed galaxies, doomed never to grow beyond a faint shimmer of stars? Or are they the key to unlocking new physics that could rewrite everything we know about dark matter and galaxy formation? One of the biggest mysteries surrounding ultra-faint dwarf galaxies is why they appear in such unusual distributions. Many of them seem to orbit larger galaxies in strange, thin, disk-like formations, something that standard models of galaxy evolution struggle to explain. According to our current understanding, dwarf galaxies should be scattered in random orbits around their host galaxies, not neatly arranged in vast, organized planes. Some researchers have suggested that these thin distributions might be the result of ancient galactic collisions, with tidal forces carving out streams of stars that later coalesced into ultra-faint dwarfs. Others believe this arrangement could be evidence of dark matter behaving in ways we don't yet understand. But what if the problem isn't with the galaxies themselves, but with our understanding of gravity? Some alternative theories propose that gravity might behave differently on cosmic scales, and ultra-faint dwarf galaxies could be the key to testing these ideas. If these galaxies are orbiting in ways that don't match the predictions of Newtonian or Einsteinian gravity, it could suggest that our theories need revising. Some astrophysicists even argue that ultra-faint dwarf galaxies could be evidence for modifications to gravity itself, hinting at new forces at play in the cosmos. Another strange property of ultra-faint dwarf galaxies is their apparent lack of gas. Most galaxies, especially smaller ones, should contain at least some amount of hydrogen gas, the raw material needed for star formation. Yet many ultra-faint dwarfs appear to be almost entirely devoid of gas, leaving astronomers puzzled. Did they lose their gas in the distant past, stripped away by the gravitational influence of larger galaxies? Or did they never have much gas to begin with, forming in environments where gas was scarce? If ultra-faint dwarfs somehow formed without much gas, it would challenge our understanding of how galaxies emerged from the early universe. This lack of gas is especially strange given the presence of heavy elements in some ultra-faint dwarfs. Normally, heavy elements, like iron and gold, are produced in stars and spread throughout a galaxy when those stars explode as supernovae. If ultra-faint dwarfs have undergone multiple generations of star formation, they should contain some residual gas enriched with these elements. Yet in many cases, the gas is completely missing, raising even more questions. Some astronomers suspect that ultra-faint dwarf galaxies might have experienced dramatic, galaxy-wide bursts of star formation in the past, which could have blown away most of their gas. If these galaxies once contained large populations of young, hot stars, then massive stellar winds and supernova explosions could have ejected gas into intergalactic space. But for this to happen on such a dramatic scale, something would have had to trigger these bursts, perhaps an ancient merger with another dwarf galaxy, or a close encounter with a much larger galaxy that disturbed the delicate balance of gas and dark matter. What makes ultra-faint dwarf galaxies even more fascinating is that they might be some of the oldest galaxies in the universe. Because they contain so few stars, those stars tend to be incredibly old, some dating back nearly to the beginning of the universe itself. If ultra-faint dwarfs truly are ancient relics, then studying them could give us a glimpse into what the first galaxies looked like before the universe was even 1 billion years old. These galaxies could be fossilized remnants of the earliest structures to form in the cosmos, providing direct insight into an era we can't study any other way. But if ultra-faint dwarf galaxies are ancient, why have they remained so small and dim? Why didn't they grow into larger galaxies over billions of years? Some scientists believe that these galaxies were simply unlucky, formed in regions of space where there wasn't enough material to grow. Others think that dark matter played a role, with unusually dense clumps of dark matter preventing normal matter from forming into larger, brighter galaxies. If that's the case, then ultra-faint dwarfs could be some of the best laboratories for studying the properties of dark matter itself. And then there's the strangest possibility of all. What if some ultra-faint dwarf galaxies aren't galaxies at all? What if they are something entirely different, something we haven't even begun to understand? Some researchers have proposed that these objects might be the visible signs of hidden, invisible structures in the universe. If dark matter forms complex, unseen halos around galaxies, then ultra-faint dwarfs might be places where normal matter has become trapped inside these halos, like stars caught in the gravitational pull of something much larger than they appear. It's also possible that some ultra-faint dwarf galaxies could be remnants of much larger galaxies that were stripped down to their barest core. If a massive galaxy collided with another galaxy billions of years ago, its outer layers of stars and gas might have been ripped away, leaving behind only a tiny remnant core, a ghost of its former self, still orbiting in the depths of space. These stripped-down remnants could be masquerading as ultra-faint dwarfs, tricking us into thinking they are small, independent galaxies when in reality they are the shattered remains of something much grander. The mystery of ultra-faint dwarf galaxies is one of the greatest unsolved puzzles in modern astrophysics. They challenge our theories of galaxy formation, dark matter, and even the fundamental laws of physics. As new telescopes and technologies come online, we may finally begin to unlock their secrets. But for now, they remain one of the universe's most enigmatic riddles. What are these galaxies really? Are they ancient fossils, the last remnants of a forgotten era? Are they the missing link between dark matter and normal matter? Or could they be something far more exotic, evidence of new physics waiting to be discovered? Whatever the answer, one thing is certain: the more we study ultra-faint dwarf galaxies, the more we realize just how much we still don't know about the universe. Ultra-faint dwarf galaxies stand as silent witnesses to a history we can barely comprehend, frozen in time as relics of the universe's infancy. Their existence is paradoxical. They are both incredibly rare and yet seemingly essential to the broader cosmic structure. The fact that they challenge so many established theories only deepens their intrigue. Are they the oldest surviving structures in the cosmos, untouched by time? Or are they remnants of once thriving galaxies that were stripped bare by the harsh forces of the universe? To truly grasp the scale of their mystery, consider how galaxies typically form. Standard cosmological models suggest that galaxies grow by accumulating gas, forming stars, and merging with other galaxies over billions of years. The largest galaxies we see today, like the Milky Way, are thought to have been built up through countless smaller mergers, with dwarf galaxies playing a crucial role in this process. But ultra-faint dwarfs don't seem to fit this pattern. They appear to have remained almost unchanged for billions of years, as if they were frozen in an early stage of development. This suggests two possibilities: either they formed in an environment that prevented them from growing, or they were once larger galaxies that lost almost everything. If they were always small, it could mean that ultra-faint dwarfs represent the very first galaxies, structures that formed in a universe still dominated by dark matter, before normal matter had a chance to clump together into larger formations. If, on the other hand, they were stripped-down remnants of larger galaxies, it raises questions about what could have caused such extreme destruction. Was it interactions with larger galaxies? Or could there be unknown cosmic forces at play? One major challenge in studying these galaxies is their extreme faintness. Unlike bright spiral galaxies or massive elliptical galaxies, ultra-faint dwarfs barely emit any light, making them incredibly difficult to detect. They often contain only a few thousand stars, compared to the hundreds of billions in a galaxy like the Milky Way. Some of them are so dim that they were only discovered in the last decade, despite being relatively close to us in cosmic terms. It's possible that many more ultra-faint dwarfs are out there, hidden in the darkness, waiting to be discovered. One of the strangest aspects of ultra-faint dwarf galaxies is their relationship with dark matter. Current models of galaxy formation suggest that dark matter plays a crucial role in shaping galaxies, acting as an invisible skeleton that helps normal matter clump together. But ultra-faint dwarfs seem to be made almost entirely of dark matter, with only a tiny sprinkling of stars embedded within them. In some cases, astronomers estimate that dark matter outweighs normal matter in these galaxies by a factor of 1,000 or more. This extreme dark matter dominance makes ultra-faint dwarfs some of the best places to study dark matter itself. Because these galaxies contain so little normal matter, they provide a rare opportunity to isolate and analyze the effects of dark matter without interference from other galactic processes. If we can understand how dark matter behaves in ultra-faint dwarfs, it could provide crucial insights into one of the biggest unsolved mysteries in physics. One of the leading theories about dark matter is that it consists of weakly interacting massive particles, or WIMPs. These hypothetical particles are thought to be incredibly difficult to detect, interacting only through gravity and the weak nuclear force. If WIMPs exist, they should be present in large quantities in ultra-faint dwarfs, potentially producing subtle effects that could be observed with precise measurements. Some researchers have even proposed using these galaxies as natural laboratories to test dark matter interactions, hoping to detect signs of dark matter annihilation or decay. But what if dark matter doesn't behave as we expect? Some alternative theories suggest that dark matter might not be made of particles at all, but rather be the result of modifications to gravity itself. If that's the case, ultra-faint dwarfs could provide the key evidence needed to test these ideas. If their motions don't match predictions based on known physics, it could indicate that our understanding of gravity is incomplete. Some theories, like modified Newtonian dynamics, (MOND), propose that gravity behaves differently at very low accelerations, which could explain the unusual properties of ultra-faint dwarfs. The distribution of ultra-faint dwarf galaxies also raises serious questions. Observations of the Milky Way's satellite galaxies have revealed that many of these dwarfs are arranged in a thin, disk-like plane rather than being randomly distributed as expected. This has led some scientists to suggest that they might not be independent galaxies at all, but rather the remnants of a past galactic collision. If a large galaxy once tore apart a smaller one, the resulting debris could have reformed into ultra-faint dwarfs, explaining their unusual arrangement. Some researchers have even proposed that ultra-faint dwarfs could be linked to ancient cosmic filaments, vast structures of dark matter and gas that crisscross the universe, forming the backbone of the cosmic web. If these galaxies formed along these filaments, it could explain why they are found in such specific patterns. This would suggest that ultra-faint dwarfs are not just isolated oddities, but key pieces of the larger puzzle of cosmic structure. Another major mystery is the presence of heavy elements in some ultra-faint dwarf galaxies. Normally, elements like iron and gold are produced in stars and spread through a galaxy when those stars explode as supernovae. But ultra-faint dwarfs have such low star formation rates that it's unclear how these elements got there. Some astronomers believe that ultra-faint dwarfs might have experienced brief but intense bursts of star formation in the past, producing enough supernovae to enrich their stars with heavy elements. But what could have triggered such bursts? Did they collide with another galaxy? Or did they pass through a region of space rich in gas that temporarily fueled star formation? Some ultra-faint dwarfs also show unusual patterns of chemical enrichment, with certain elements appearing in unexpected ratios. This suggests that these galaxies may have undergone unique evolutionary histories, possibly influenced by factors we don't yet understand. If ultra-faint dwarfs were some of the first galaxies to form, their chemical compositions could provide crucial clues about the early universe, offering a direct glimpse into the conditions that existed just a few 100 million years after the Big Bang. But perhaps the biggest question of all is, why do ultra-faint dwarf galaxies exist at all? In many ways, their presence contradicts what we think we know about galaxy formation. They shouldn't be able to survive for billions of years without being disrupted or absorbed by larger galaxies. They shouldn't be able to retain enough dark matter to remain gravitationally bound despite their low masses. And yet they are there, stubbornly defying our expectations. Some astronomers have even speculated that ultra-faint dwarfs could be evidence of entirely new physics. If they contain more dark matter than expected, it might suggest that dark matter behaves differently in extreme environments. If their stars are arranged in unusual patterns, it could indicate that galaxy formation works in ways we haven't yet understood. Every new discovery about these galaxies raises more questions than it answers, making them one of the most tantalizing puzzles in modern astrophysics. As new telescopes and observational techniques improve, we may finally begin to unravel the secrets of these enigmatic galaxies. The upcoming Vera C. Rubin Observatory, for example, is expected to discover even more ultra-faint dwarfs, potentially revealing new patterns in their distribution. Meanwhile, advances in computer simulations are allowing scientists to model the formation of these galaxies in greater detail, testing different theories about their origins. But for now, ultra-faint dwarf galaxies remain one of the universe's greatest mysteries. Are they the long-lost fossils of the first galaxies? Are they dark matter laboratories, holding the key to understanding the invisible substance that makes up most of the universe? Or are they something even stranger, evidence of unknown forces shaping the cosmos in ways we can't yet comprehend? Whatever the answer, one thing is certain: the deeper we look into the darkness of space, the more mysteries we find waiting for us. Ultra-faint dwarf galaxies challenge our understanding of how the universe works at every level. Their existence defies the standard models of galaxy formation, their behavior suggests unknown interactions with dark matter, and their sheer rarity raises the question of whether we are only seeing the tip of an enormous cosmic iceberg. If there are more of them out there, hidden in the depths of space, beyond the reach of our current technology, what might they reveal about the origins of the cosmos itself? One of the most intriguing aspects of these galaxies is their sheer resilience. In a universe filled with chaos, where massive galaxies collide, stars explode, and black holes devour everything in their vicinity, ultra-faint dwarfs have somehow survived for billions of years. How? By all accounts, they should have been destroyed long ago, their stars scattered into intergalactic space. But they remain, frozen in time, as if they have been protected by some unseen force. Some researchers believe that dark matter is the answer to this mystery. If these galaxies are made up of significantly more dark matter than ordinary matter, then their gravitational structure could be far stronger than we realize. This would mean that even though they appear fragile, barely held together by a few thousand stars, they might actually be among the most gravitationally stable objects in the universe. But this raises another question: if ultra-faint dwarfs contain so much dark matter, why don't we see more of them? Shouldn't there be countless more lurking in the void, waiting to be discovered? One possibility is that we simply haven't looked hard enough. Many ultra-faint dwarfs have only been detected in recent years, and even then, only because astronomers knew exactly where to look, near large galaxies like the Milky Way and Andromeda. But what if they exist in much greater numbers, scattered across the vast emptiness of intergalactic space? If so, they could be acting as cosmic signposts, tracing the hidden scaffolding of dark matter that holds the universe together. Another possibility is that these galaxies are disappearing over time. While they may have been more common in the past, their numbers could be dwindling as they slowly fade into obscurity. This could happen in several ways. If ultra-faint dwarfs are gravitationally bound to larger galaxies, they could be slowly losing their stars due to tidal interactions. Over millions or billions of years, this process could strip them down to nothing, leaving behind only a dark matter halo with no visible trace of its original structure. Alternatively, some ultra-faint dwarfs might be merging with one another, forming slightly larger but still faint galaxies. If this is the case, then what we see today might be only a fraction of what once existed, meaning that the universe may have once been teeming with even more of these strange, barely there galaxies. But perhaps the most exciting possibility is that ultra-faint dwarfs hold the key to understanding something even more fundamental about the cosmos. If they contain more dark matter than expected, or if their stars move in ways that defy our current models of gravity, then they could provide evidence for new physics. Some researchers have even suggested that studying these galaxies could help us determine whether dark matter interacts with itself in ways we don't yet understand. For example, if dark matter can scatter or interact in subtle ways, it might explain why ultra-faint dwarfs seem to have such unusual properties. Some observations suggest that dark matter in these galaxies is not perfectly uniform but clumped in unexpected ways. If this is true, It could hint at new types of dark matter interactions, ones that go beyond the simple idea of weakly interacting particles. Another strange feature of ultra-faint dwarfs is their star formation history. Unlike normal galaxies, which continuously form new stars over billions of years, ultra-faint dwarfs seem to have had only brief, sporadic bursts of star formation, with long periods of inactivity in between. This suggests that something, perhaps the environment around them, or their own internal dynamics, is preventing them from forming stars in the same way as other galaxies. One theory is that ultra-faint dwarfs were quenched early in their history by cosmic reionization, a process that occurred when the first stars and galaxies flooded the universe with high-energy radiation, stripping away gas and preventing new stars from forming. If this is the case, then these galaxies could be among the oldest surviving relics of the early universe, frozen in time since the end of the cosmic dark ages. Another possibility is that these galaxies were stripped of their gas by interactions with larger galaxies. If an ultra-faint dwarf passed too close to a massive galaxy like the Milky Way, its gas could have been pulled away, leaving it unable to form new stars. This could explain why some ultra-faint dwarfs appear completely devoid of gas, while others still retain a small amount. But there's an even stranger possibility. What if some ultra-faint dwarfs never contain much normal matter to begin with? What if they are primarily composed of dark matter, with only a handful of stars sprinkled throughout? If this is the case, then ultra-faint dwarfs could be the closest thing we have to pure, dark matter galaxies, providing a unique laboratory for testing the nature of this elusive substance. In recent years, astronomers have begun using ultra-faint dwarfs to search for signs of dark matter annihilation. If dark matter particles can collide and annihilate one another, they should produce faint but detectable signals, such as high-energy gamma rays. By studying ultra-faint dwarfs, researchers hope to find indirect evidence of dark matter interactions that could help us determine what dark matter is actually made of. So far, the results have been inconclusive. While some signals have been detected, they are not strong enough to provide definitive proof. But as telescopes become more sensitive, we may finally get the breakthrough we've been looking for, one that could revolutionize our understanding of the universe. One of the biggest challenges in studying ultra-faint dwarfs is simply finding them. Because they are so faint, they are nearly impossible to detect unless they are relatively close to us. The Milky Way's halo likely contains many more of these galaxies than we currently know about, but they remain hidden in the darkness, waiting to be uncovered. Upcoming surveys, such as those conducted by the Vera C. Rubin Observatory, are expected to dramatically increase the number of known ultra-faint dwarfs. This will allow astronomers to map out their distribution in greater detail, helping us determine whether their unusual arrangements are the result of unknown cosmic forces or simply a statistical fluke. But even if we do find more of these galaxies, the deeper question remains: why are they so different from other galaxies? Why do they contain so much dark matter? And what can they tell us about the early universe? As we continue to explore the cosmos, ultra-faint dwarfs may prove to be the missing puzzle pieces that finally unlock the secrets of dark matter, galaxy formation, and the fundamental nature of the universe itself. They are among the strangest and most mysterious objects we've ever encountered, but perhaps, in their quiet solitude, they hold the answers we've been searching for all along. Ultra-faint dwarf galaxies are more than just a curiosity in the vast cosmos. They might be the key to understanding the structure of the universe itself. Their very existence challenges the way we think about galaxy formation, dark matter, and the forces that shape the cosmos. While they appear small and fragile, they have survived for billions of years, suggesting that something powerful is holding them together. But what if they are just the visible remnants of a much larger and more complex cosmic mystery? One of the biggest questions surrounding ultra-faint dwarfs is whether they are truly galaxies in the traditional sense, or if they represent an entirely new category of cosmic structure. In standard galaxy formation models, galaxies grow by accumulating gas and forming stars, often merging with other galaxies to become larger over time. But ultra-faint dwarfs don't seem to follow this pattern. They have barely any gas left, they contain very few stars, and they don't seem to have undergone major mergers. This suggests that their formation process was very different from that of normal galaxies. Some astronomers believe that ultra-faint dwarfs are the remnants of primordial galaxies, some of the first structures to form in the universe after the Big Bang. If this is true, then they could provide a direct window into the early universe, preserving information about conditions that existed over 13 billion years ago. Unlike large galaxies, which have undergone significant changes due to mergers, supernova explosions, and star formation, ultra-faint dwarfs might have remained largely unchanged, making them some of the best time capsules we have for studying the dawn of the cosmos. But there's another possibility, one that is even more bizarre. What if ultra-faint dwarfs aren't just old, but are instead artificial? This might sound like science fiction, but some researchers have speculated that these galaxies could be evidence of advanced alien civilizations at work. If a civilization were capable of manipulating dark matter or controlling the structure of a galaxy, they might be able to create ultra-faint dwarfs as a way of hiding their presence, or using them for unknown purposes. While this idea remains purely hypothetical, it raises fascinating questions about what kinds of astrophysical engineering might be possible on cosmic scales. Regardless of their origin, ultra-faint dwarfs remain incredibly difficult to detect. They are so faint that they barely emit any light, making them almost invisible against the backdrop of the universe. In fact, some of the ones we have discovered were only found because astronomers were specifically looking for them in the regions surrounding the Milky Way. This means that there could be thousands, or even millions, of ultra-faint dwarfs scattered throughout the universe that we simply haven't been able to see yet. New telescopes and observational techniques are helping astronomers hunt for these elusive galaxies. The Vera C. Rubin Observatory, set to begin operations soon, will conduct an unprecedented survey of the night sky, potentially revealing many more ultra-faint dwarfs in the process. Meanwhile, advancements in radio astronomy and gravitational lensing techniques could provide alternative ways to detect these objects, even if they remain hidden in visible light. But the real question remains, why do ultra-faint dwarfs exist at all? In standard cosmology, galaxies form through the collapse of massive clouds of gas, with dark matter playing a crucial role in binding them together. However, ultra-faint dwarfs contain so little visible matter that their very existence seems improbable. If they formed the same way as normal galaxies, they should have been disrupted long ago. If they formed differently, we need to rethink our entire understanding of how galaxies emerge and evolve. One possibility is that ultra-faint dwarfs are the last survivors of a population of galaxies that were once much more common. Perhaps in the early universe, many such galaxies existed, but most of them were eventually absorbed into larger galaxies or torn apart by cosmic forces. The few that remain today might be the last remnants of this ancient population, existing on borrowed time before they too are destroyed or become completely invisible. Another possibility is that ultra-faint dwarfs are somehow protected by dark matter in ways we don't yet understand. If dark matter interacts with itself in subtle ways, beyond simply exerting gravitational force, it could create pockets of stability that prevent these galaxies from being destroyed. Some theories even suggest that dark matter could form structures that act like invisible scaffolding, holding these galaxies together despite their lack of visible material. If this is true, then ultra-faint dwarfs could be the best natural laboratories for studying the nature of dark matter itself. By measuring the movements of stars within these galaxies, astronomers can infer the properties of the invisible matter surrounding them. If the dark matter behaves in unexpected ways, such as clumping together or interacting through forces beyond gravity, it could provide crucial clues about what dark matter actually is. Some of the most detailed studies of ultra-faint dwarfs have already hinted at anomalies in dark matter behavior. In some cases, the distribution of dark matter in these galaxies does not match predictions from standard cosmological models. Instead of forming smooth halos around the galaxies, dark matter appears to be more concentrated in certain areas, suggesting that it may interact in ways we don't yet understand. This has led some researchers to propose alternative explanations for what dark matter might be. Instead of being made of a single type of weakly interacting particle, dark matter could be composed of multiple different components, each with its own unique properties. Some models even suggest that dark matter could be a type of hidden sector physics, meaning that it might consist of particles that interact with one another through unknown forces. If these theories are correct, ultra-faint dwarfs could hold the key to one of the biggest unsolved mysteries in physics. By studying these galaxies in greater detail, we might finally unlock the secrets of dark matter and understand the true structure of the universe. But even beyond their role in dark matter research, ultra-faint dwarfs challenge our understanding of what a galaxy is. In some ways, they are unlike any other type of galaxy we know. They contain so few stars that they sometimes blur the line between being a galaxy and simply being a collection of loosely bound stars. Their extreme faintness makes them difficult to detect, meaning that we might only be seeing a fraction of what actually exists. And their resilience suggests that they are held together by forces we don't yet fully understand. As astronomers continue to search for more of these galaxies, the discoveries they make could reshape our understanding of cosmic evolution. If ultra-faint dwarfs turn out to be more common than we expect, it could indicate that the universe is filled with hidden structures that have so far remained undetected. If they turn out to be rare, it could suggest that we are seeing the last remnants of a dying population of ancient galaxies. Either way, ultra-faint dwarfs remind us of how much we still have to learn about the cosmos. They are silent, hidden, and nearly invisible, but they may hold the answers to some of the biggest questions in science. And if we ever do find definitive proof that these galaxies contain something truly unexpected, whether it be new types of dark matter, exotic physics, or even the remnants of ancient civilizations, it could change everything we thought we knew about the universe. Ultra-faint dwarf galaxies may be small, but their implications for astrophysics are massive. They sit at the intersection of some of the biggest questions in cosmology, from the nature of dark matter to the very process by which galaxies form. Despite their apparent insignificance in size and brightness, they may hold the key to unlocking secrets that have baffled scientists for decades. The more we study them, the more they seem to defy expectations, leaving us with more questions than answers. One of the strangest aspects of ultra-faint dwarfs is how they are distributed around the Milky Way. These galaxies tend to cluster in unexpected patterns, often aligned in thin planes rather than being randomly scattered, as conventional cosmology would predict. This so-called plane of satellites problem has led some astronomers to question whether our models of galaxy formation are incomplete. If galaxies form purely due to gravitational collapse and the influence of dark matter, their distribution should be more randomized. The fact that ultra-faint dwarfs appear to follow structured alignments suggests that something else might be shaping their placement in the universe. Some theories propose that these galaxies were not formed where we see them today but were instead captured by the Milky Way at some point in the past. If that's true, then their arrangement might be the result of ancient interactions between galaxies, potentially involving unknown gravitational forces or even exotic physics. Others have suggested that these alignments could be evidence of unseen structures in the dark matter distribution around the Milky Way, structures that are not currently accounted for in standard cosmological models. Adding to the mystery, some ultra-faint dwarf galaxies seem to be experiencing an unusually high rate of dark matter stripping. In other words, as they orbit the Milky Way, they appear to be losing large amounts of their dark matter halos, leaving behind only the bare minimum of stars and visible material. The cause of this phenomenon is unclear. It could be due to gravitational interactions with the Milky Way itself, slowly tearing these galaxies apart over billions of years. But some researchers argue that the process is too efficient to be explained by gravity alone, hinting that other forces, possibly new interactions within dark matter, could be at play. If dark matter has more properties than just gravitational attraction, it might be capable of dissipating or interacting with itself in ways that could explain why ultra-faint dwarfs are losing so much of it. This idea aligns with some alternative dark matter theories, such as self-interacting dark matter, SIDM, which suggests that dark matter particles can collide and exchange energy in ways that affect their distribution within galaxies. If true, then ultra-faint dwarfs might be some of the best places to observe this process in action, providing indirect evidence of dark matter behaving in ways we haven't yet fully understood. Beyond their dark matter mysteries, ultra-faint dwarfs also defy expectations when it comes to their star formation history. Unlike typical galaxies, which go through multiple periods of star formation, ultra-faint dwarfs appear to have experienced only a single brief burst of star formation early in their history. This suggests that something abruptly halted their ability to create new stars, leaving them as ghostly relics of a bygone era in cosmic history. One possible explanation is that these galaxies were stripped of their gas by interactions with larger galaxies. In the early universe, when galaxies were forming at a rapid pace, smaller galaxies often fell into the gravitational influence of larger ones. As they did, powerful tidal forces could have pulled away their gas, preventing them from forming new stars. Another possibility is that an external cosmic event, such as a period of intense radiation from early quasars or the first massive stars, heated up or expelled the gas within these galaxies, effectively shutting down star formation forever. Yet another theory suggests that ultra-faint dwarfs never had much gas to begin with. If these galaxies formed in regions where the density of gas was unusually low, they might have only been able to form a small number of stars before running out of material. This would make them fundamentally different from most other galaxies, suggesting that there may be multiple distinct ways that galaxies can form and evolve. A particularly intriguing idea is that ultra-faint dwarfs could be some of the earliest galaxies to form in the universe, true fossils of the first galaxies ever created. If so, then their chemical composition should reflect this, containing only the very first elements produced in the early universe, such as hydrogen and helium, with very little of the heavier elements produced by later generations of stars. Observations so far support this idea, with many ultra-faint dwarfs containing extremely low levels of metals compared to typical galaxies. This suggests that they formed at a time before heavier elements had become widespread in the universe, reinforcing the idea that they are some of the oldest surviving structures in existence. If ultra-faint dwarfs truly are among the first galaxies, then studying them is like looking back in time to the earliest moments of the universe. They provide a glimpse into what galaxies might have been like before the Milky Way, before the large spiral and elliptical galaxies that dominate the cosmos today. Understanding their history could help answer fundamental questions about how the first galaxies formed, how they evolved, and how they eventually gave rise to the complex structures we see in the universe today. Some astronomers have even proposed that ultra-faint dwarfs could help solve the missing satellites problem, one of the biggest mysteries in cosmology. According to computer simulations, the Milky Way should have many more satellite galaxies than we currently observe. The fact that we see so few suggests that either our understanding of galaxy formation is incomplete, or that many of these galaxies are simply too faint for us to detect. Ultra-faint dwarfs might be the missing satellites we've been looking for, providing evidence that the universe is filled with far more small galaxies than we previously realized. But this raises another unsettling possibility. What if ultra-faint dwarfs are just the tip of the iceberg? What if there are even fainter, even more elusive structures out there that we simply haven't been able to detect yet? If the cosmos is filled with galaxies that emit almost no light, then our picture of the universe is incomplete in ways we can't even begin to imagine. There could be entire populations of hidden galaxies, lurking beyond our current observational capabilities, shaping the cosmos in ways we don't yet understand. As telescopes improve and our ability to detect faint objects increases, we may start to uncover even more ultra-faint dwarfs, potentially rewriting our understanding of galaxy formation and dark matter in the process. Future observatories like the Vera C. Rubin Observatory and the James Webb Space Telescope will be crucial in this effort, allowing astronomers to peer deeper into space and detect objects that were previously invisible to us. The more we learn about ultra-faint dwarf galaxies, the more it becomes clear that they are far more than just cosmic oddities. They are fundamental pieces of the puzzle in understanding the universe's structure, its history, and its most elusive components. Whether they turn out to be remnants of the first galaxies, evidence of unknown physics, or something even stranger, one thing is certain: they are among the most mysterious objects in the cosmos, and their secrets are only just beginning to be uncovered. The search for more ultra-faint dwarf galaxies is not just about filling in gaps in our cosmic map, it's about challenging the very foundations of our understanding of the universe. These tiny galaxies, barely visible against the cosmic backdrop, hold clues to some of the deepest mysteries in astrophysics. Each new discovery brings fresh questions. Why do these galaxies exist in such extreme conditions? What role do they play in the evolution of larger galaxies like the Milky Way? And could they be the key to finally understanding the nature of dark matter? One of the biggest puzzles surrounding ultra-faint dwarfs is their apparent abundance, or lack thereof. According to simulations based on the widely accepted lambda-cold dark matter model of cosmology, the Milky Way should have thousands of small satellite galaxies orbiting it. Yet, only a few dozen ultra-faint dwarfs have been detected so far. This discrepancy, known as the missing satellites problem, suggests that something is either preventing these galaxies from forming or making them incredibly difficult to detect. Some researchers argue that the problem is observational. We simply don't have the technology to see the majority of these tiny galaxies yet. Ultra-faint dwarfs are, by definition, incredibly dim, with very few stars. If many of them exist in regions with dense interstellar dust or are spread out in ways that make them hard to distinguish from the cosmic background, they could be hiding in plain sight. Upcoming telescopes like the Vera C. Rubin Observatory, which is designed to detect faint and fast-moving objects, may reveal an entire hidden population of these galaxies. But there's another possibility. What if these galaxies don't exist in the numbers that our models predict? If the missing satellites problem is real, it could mean that our understanding of galaxy formation is flawed. One possible explanation is that dark matter behaves differently than we think. The standard model assumes that dark matter is cold, meaning that it moves slowly in clumps together, forming the seeds for galaxy formation. But if dark matter is instead warm, or even self-interacting, it could behave in ways that prevent small galaxies from forming in the first place. Self-interacting dark matter, SIDM, is one of the most intriguing alternatives to the standard model. In this theory, dark matter particles can collide and transfer energy, preventing them from clumping into small, dense structures. This would naturally explain why there are fewer ultra-faint dwarfs than expected. They simply never formed in large numbers because dark matter couldn't condense into small halos efficiently. Some ultra-faint dwarfs that we do see may be survivors of an early era in which many other small galaxies were disrupted or dissolved by these dark matter interactions. Another theory suggests that ultra-faint dwarfs do exist in large numbers but remain dark, meaning they contain little to no visible stars. If this is true, then the universe could be filled with dark galaxies, made almost entirely of dark matter, with only a tiny fraction of them forming enough stars to be detectable. This idea is difficult to prove, but future surveys searching for indirect signs of these dark galaxies, such as gravitational lensing effects, may provide evidence for their existence. Even the ultra-faint dwarfs that we do detect challenge our understanding of galactic evolution. Many of them appear to be chemically primitive, containing stars with extremely low metal content. In astrophysics, metals refer to elements heavier than hydrogen and helium, which are created in the cores of stars and spread throughout the universe when those stars explode as supernovae. The fact that ultra-faint dwarfs contain so few heavy elements suggests that they stopped forming stars very early in cosmic history, perhaps within the first billion years after the Big Bang. If ultra-faint dwarfs truly are relics of the early universe, studying them is like opening a time capsule from the dawn of cosmic history. By analyzing the chemical makeup of their stars, astronomers can infer what conditions were like in the universe's infancy. Some of these galaxies may even contain population 3 stars, the very first generation of stars ever formed, which are thought to be extremely massive and composed entirely of hydrogen and helium. If we could identify an ultra-faint dwarf containing population 3 stars, it would be one of the most significant discoveries in astronomy, providing direct insight into how the first stars and galaxies came into existence. But the mysteries of ultra-faint dwarfs go beyond their formation. Their current survival is equally puzzling. Many of these galaxies orbit the Milky Way at distances where they should be strongly affected by tidal forces, gravitational interactions that should, in theory, tear them apart over billions of years. Yet, despite their fragile appearance, they persist. Some astronomers believe that dark matter is playing a protective role, providing enough gravitational glue to keep these galaxies from being destroyed. But if dark matter is truly this dominant, then why are some ultra-faint dwarfs losing their dark matter halos at an accelerated rate? One of the most intriguing cases is Tucana 3, an ultra-faint dwarf galaxy that appears to be actively being torn apart by the Milky Way's gravitational pull. Long stellar streams extend from the main body of the galaxy, indicating that its stars are being stripped away. This could be the final stage in the life of a dwarf galaxy, an example of what happens when a tiny galaxy gets too close to a much larger one. However, what remains unclear is why some ultra-faint dwarfs experience this fate, while others seem to remain intact. One possibility is that different ultra-faint dwarfs have different dark matter compositions. If dark matter comes in multiple forms, some of which are more resistant to tidal disruption than others, then this could explain why some galaxies hold together while others dissolve. Another possibility is that some ultra-faint dwarfs are, artificially, stabilized by interactions with other satellite galaxies or with unseen clumps of dark matter in the Milky Way's halo. The nature of ultra-faint dwarfs has even led some researchers to propose that they could be made up of primordial black holes, small black holes formed in the earliest moments of the universe, long before the first stars appeared. If true, this would be groundbreaking, as it would provide evidence for a long-debated theory that black holes could have been the first structures to form in the cosmos. These black holes could act as the gravitational cores around which ultra-faint dwarfs formed, influencing their evolution in ways we do not yet understand. The study of ultra-faint dwarf galaxies is still in its infancy, and every new discovery seems to raise more questions than answers. Are they the missing satellites that cosmologists have been searching for? Are they fossilized remnants of the first galaxies? Are they evidence that dark matter behaves in ways we haven't predicted? Or do they hint at even more exotic possibilities, like the existence of unknown physics governing the structure of the cosmos? As our telescopes and observational techniques improve, we may finally begin to unravel the mysteries surrounding these elusive galaxies. Upcoming missions will scan the sky for faint objects with unprecedented precision, potentially revealing hundreds, if not thousands, of ultra-faint dwarfs that have remained hidden until now. But even then, the deeper mystery remains: what if ultra-faint dwarfs are just one piece of an even larger cosmic puzzle? If we've only just begun to detect the faintest galaxies, what else is lurking out there in the darkness, waiting to be discovered? The search for ultra-faint dwarf galaxies is more than just a quest for missing pieces in our cosmic puzzle. It's a confrontation with the limits of our understanding of the universe itself. Every time we point our telescopes at the sky, we're looking into the past, peeling back layers of cosmic history. But what happens when the universe doesn't behave the way we expect? What if these tiny galaxies are telling us something fundamental about reality that we're still missing? One of the biggest challenges in studying ultra-faint dwarfs is simply finding them. Their low brightness and small size make them incredibly difficult to detect, even with the most powerful telescopes. Unlike larger galaxies, which shine brightly with billions of stars, these dwarfs are made up of only a few thousand to a few 100,000 stars, barely enough to register against the cosmic background. It's like trying to find a single dim candle flickering in a vast, dark forest. To overcome this challenge, astronomers use a variety of techniques. One of the most effective is star counting. By analyzing images of the sky and looking for groups of stars that move together, researchers can identify potential ultra-faint dwarfs. This method relies on the fact that stars in a galaxy share a common motion and chemical signature. But even this approach has its limits, especially when dealing with galaxies that are spread out or hidden behind interstellar dust. Another method involves gravitational lensing, a phenomenon where the gravity of a massive object bends and magnifies the light from objects behind it. If an ultra-faint dwarf passes in front of a bright background source, its gravitational pull can subtly distort the light, making it possible to infer the presence of the otherwise invisible galaxy. This technique has been used to detect distant galaxies at the edge of the observable universe, and it may prove useful in uncovering more ultra-faint dwarfs in the future. But even when we do find these galaxies, the mysteries don't stop there. One of the strangest things about ultra-faint dwarfs is their extreme dark matter content. Unlike normal galaxies, where dark matter makes up a significant but not overwhelming portion of the mass, ultra-faint dwarfs are thought to be almost entirely dominated by dark matter. In some cases, they contain hundreds or even thousands of times more dark matter than visible matter. This raises a fundamental question: why? One theory is that ultra-faint dwarfs are some of the oldest galaxies in the universe, formed when dark matter first began to collapse into structures. These galaxies may have started forming stars billions of years ago, but were later stripped of their gas and left with only a small number of ancient stars. This would explain their faintness and high dark matter content, as they would essentially be dark matter fossils from the early universe. Another possibility is that ultra-faint dwarfs are relics of a different kind of dark matter interaction. Some researchers believe that dark matter may not be entirely passive but could interact with itself in ways we don't yet understand. If dark matter particles can collide and transfer energy, it could change the way small galaxies evolve, leading to the formation of ultra-faint dwarfs that are heavily dominated by dark matter. This idea is especially intriguing because it ties into the broader mystery of the missing satellites problem. If dark matter behaves differently on small scales than on large scales, it could explain why we see fewer ultra-faint dwarfs than expected. It could also mean that dark matter isn't as cold as we thought, that is, it doesn't clump together as easily, making it harder for small galaxies to form. Some astronomers have even suggested that ultra-faint dwarfs could be a window into an entirely new form of physics. If they contain unusual dark matter properties or behave in unexpected ways, they could point to new fundamental forces at work in the universe. For example, if dark matter can decay or interact with itself in certain conditions, it could leave behind unique signatures in these galaxies, signatures that might help us finally understand what dark matter really is. But perhaps the strangest possibility of all is that ultra-faint dwarfs are connected to a completely different kind of unseen matter. Some fringe theories propose that these galaxies could be influenced by primordial black holes, tiny black holes formed in the earliest moments of the universe. If these black holes exist in large numbers, they could act as seeds, around which ultra-faint dwarfs formed. This would mean that these galaxies are not just dark matter dominated, but possibly black hole dominated, a concept that would challenge everything we think we know about galaxy formation. As we continue to discover more ultra-faint dwarfs, each new finding raises more questions than answers. Why do some of these galaxies survive while others are torn apart? Why do some contain small pockets of gas while others appear completely barren? Could there be ultra-faint dwarfs lurking in intergalactic space, far from the influence of larger galaxies? One of the most promising avenues for answering these questions is the upcoming Vera C. Rubin Observatory, which is set to begin operations in the near future. This telescope will conduct an unprecedented survey of the sky, capable of detecting faint and fast-moving objects with incredible precision. If ultra-faint dwarfs are more common than we currently believe, the Rubin Observatory could reveal hundreds or even thousands of them, shedding light on their true nature. At the same time, astronomers are looking to other galaxies beyond the Milky Way to see if similar ultra-faint dwarfs exist elsewhere. If they do, it could confirm that these galaxies are a universal feature of cosmic evolution rather than a quirk of our own galaxy's history. But even with all these advancements, the ultimate question remains: what are ultra-faint dwarf galaxies really telling us about the universe? Are they the missing pieces in our models of galaxy formation, or do they hint at deeper, more fundamental mysteries? If dark matter behaves differently in these galaxies, what does that mean for our understanding of the cosmos as a whole? The search for answers continues, and with every new discovery, we come one step closer to understanding the invisible forces shaping the universe. But the more we learn, the more we realize how much we still don't know. Ultra-faint dwarf galaxies may be small, but their implications are enormous. They challenge our theories, push the boundaries of our knowledge, and remind us that even in the vastness of space, some of the biggest mysteries come in the smallest packages. And perhaps the biggest mystery of all is this: if these tiny galaxies are telling us something new about the nature of dark matter, then what other secrets are hidden in the dark? What else are we missing? The puzzle of ultra-faint dwarf galaxies forces us to question whether our current understanding of the cosmos is even close to complete. These small, ghostly galaxies don't just hint at missing pieces in our theories. they practically scream that something fundamental is off. One of the most baffling aspects of ultra-faint dwarfs is how they interact with their environment. Normally, galaxies that come too close to a larger galaxy like the Milky Way get disrupted by tidal forces. The gravitational pull of the larger galaxy stretches and distorts them, sometimes even tearing them apart completely. Yet, some ultra-faint dwarfs appear to have survived despite being in regions where they should have been destroyed. Why? Some astronomers believe that dark matter might be playing a protective role. If these galaxies are composed almost entirely of dark matter, their strong gravitational binding could make them more resistant to disruption. But that raises another question: why don't we see more of them? If dark matter makes them so stable, shouldn't there be more ultra-faint dwarfs than we currently observe? This brings us to another possibility. Maybe some ultra-faint dwarfs are simply invisible to us. If they contain even less visible matter than we think, they could be nothing more than loose collections of dark matter, completely undetectable with current telescopes. These dark galaxies would be an entirely new class of objects, galaxies without stars. The idea sounds extreme, but it's not impossible. In fact, some simulations of galaxy formation predict that many dwarf galaxies could exist in this ghostly, starless state. The idea of hidden galaxies made entirely of dark matter is tantalizing because it could explain why we see fewer ultra-faint dwarfs than expected. Maybe they're out there, but they're just too dark to see. This would mean that our surveys of the universe are missing a huge portion of the cosmic landscape, an entire population of galaxies hiding in plain sight. But how do we prove that these invisible galaxies exist? One possible method is through their gravitational influence. If an ultra-faint dwarf passes in front of a distant star, its gravity could cause a tiny shift in the star's light, a phenomenon known as gravitational microlensing. By searching for these subtle distortions, astronomers might be able to detect dark galaxies even if they contain no visible stars. Another way to hunt for these ghostly galaxies is by studying the motion of nearby stars. If a large clump of dark matter is present, it should exert a gravitational pull on surrounding objects, affecting their movements. By carefully mapping the motion of stars in the Milky Way, astronomers might be able to infer the presence of unseen ultra-faint dwarfs lurking in the background. But perhaps the strangest possibility is that some ultra-faint dwarfs aren't just missing visible matter. They might be missing dark matter too. A handful of dwarf galaxies have been discovered that appear to contain almost no dark matter at all. This is deeply puzzling because, according to our current theories, dark matter is the glue that holds galaxies together. Without it, a galaxy's stars should just drift apart. How is this possible? One idea is that these galaxies might have once been normal but were stripped of their dark matter by interactions with larger galaxies. If they pass too close to a massive galaxy like the Milky Way, the gravitational encounter could have removed most of their dark matter, leaving behind only a thin scattering of stars. Another possibility is that we don't fully understand how dark matter behaves. If dark matter can interact with itself in ways we don't yet grasp, it might be able to escape from galaxies under certain conditions. Some exotic theories suggest that dark matter might even decay over time, slowly disappearing from the universe. If that's true, ultra-faint dwarfs with missing dark matter could be the first direct evidence of this process. But what if we're thinking about this all wrong? What if ultra-faint dwarfs are revealing something even bigger, something that shakes the foundation of physics itself? Some radical theories suggest that the unusual properties of ultra-faint dwarfs could be evidence that our understanding of gravity is incomplete. According to an idea known as modified Newtonian dynamics, (MOND), gravity doesn't always behave the way we expect, especially on very small scales. If this theory is correct, then the strange behavior of ultra-faint dwarfs might not be due to dark matter at all. It might be because gravity itself works differently in these environments. This is a highly controversial idea, but if proven true, it would mean that our entire model of the universe needs to be rewritten. It would mean that the laws of physics we take for granted, laws that have successfully explained everything from planetary motion to the expansion of the universe, might not be quite right after all. As we continue to push the boundaries of what we know, one thing is clear: ultra-faint dwarf galaxies are far more than just cosmic oddities. They are windows into the unknown, revealing cracks in our understanding of the universe. They challenge our models, force us to question long-held assumptions, and may ultimately lead us to discoveries that change everything. And yet, despite all our efforts, the biggest questions remain unanswered. What are these galaxies really telling us? Are they the key to unlocking the secrets of dark matter, or do they hint at an even deeper mystery lurking in the cosmos? Could they be relics of a time before galaxies as we know them even existed, or are they something entirely different, something we haven't even begun to imagine? One thing is certain: the more we learn about ultra-faint dwarfs, the more we realize how much we still don't know. They remind us that the universe is vast, strange, and full of surprises. They challenge us to keep searching, to keep questioning, and to never assume that we have all the answers. And perhaps, just perhaps, they are the first glimpse of something even more extraordinary waiting to be discovered, something hidden in the darkness, just beyond the edge of what we can see. The mystery of ultra-faint dwarf galaxies forces us to reconsider not only the nature of dark matter but also the way galaxies form and evolve. These tiny galaxies are unlike anything we expected to find, and the deeper we look, the stranger they become. If they truly are relics from the early universe, untouched by time, then studying them could provide the closest thing we have to a time machine, offering a glimpse into the conditions that shaped everything we see today. One of the most perplexing aspects of these galaxies is their sheer scarcity. According to our best models of cosmology, the universe should be teeming with thousands, maybe even millions, of dwarf galaxies. The lambda cold dark matter model, the dominant theory that explains how large-scale cosmic structures form, predicts that small galaxies should be everywhere. But when astronomers go out and look for them, they find far fewer than expected. This is known as the missing satellites problem. If the lambda cold dark matter model is correct, then the Milky Way alone should have hundreds of ultra-faint dwarf galaxies orbiting around it. Instead, we've only found a few dozen. Where are the rest? Have we simply failed to detect them, or is something fundamentally wrong with our understanding of how galaxies form? One possible explanation is that these galaxies are hidden, either because they contain too few stars to be detected or because they're composed mostly of dark matter, making them practically invisible. Some researchers have even proposed that ultra-faint dwarfs might be composed of a different kind of dark matter altogether, one that interacts with itself in unexpected ways. If true, this could mean that our entire understanding of dark matter is incomplete, and that we may need to rethink one of the most fundamental building blocks of the universe. But what if the missing satellites problem isn't just about dark matter? What if the reason we don't see as many dwarf galaxies as we expect is because something is actively destroying them? Some scientists believe that powerful bursts of radiation from early galaxies could have heated up the surrounding gas, preventing dwarf galaxies from forming in the first place. This process, known as reionization suppression, suggests that the first galaxies may have wiped out many of their smaller neighbors before they even had a chance to develop. Another theory suggests that interactions with larger galaxies could be responsible. If a dwarf galaxy comes too close to the Milky Way, its stars and gas can be stripped away by gravitational forces, leaving behind only a dark matter core. Over time, these stripped remnants could become nearly impossible to detect, explaining why we see fewer dwarfs than expected. Yet, even with these explanations, many questions remain. Why do some ultra-faint dwarfs seem to have survived against all odds, while others have vanished? What determines whether a dwarf galaxy will endure or be torn apart? And perhaps most intriguingly, could there be an entirely new force or phenomenon at play that we have yet to discover? One particularly bizarre possibility is that ultra-faint dwarfs are evidence of an unknown interaction between dark matter and regular matter. Some theories propose that dark matter isn't completely passive. It might have subtle, yet powerful, effects on the galaxies around it. If dark matter can influence the way stars form or prevent gas from collapsing into new galaxies, it could explain why some ultra-faint dwarfs exist while others don't. But what if the strangeness of ultra-faint dwarfs isn't about dark matter at all? What if these galaxies are remnants of an earlier cosmic structure, something that predates the galaxies we see today? Some astronomers have speculated that ultra-faint dwarfs might be the remains of primordial galaxies, structures that formed before the first major galaxies ever took shape. If true, then these tiny galaxies would be the oldest living fossils in the universe, offering a direct link to a time before the Milky Way even existed. The possibility of primordial galaxies raises another fascinating question. Could ultra-faint dwarfs contain clues about the first stars in the universe? These ancient stars, known as population 3 stars, were vastly different from the stars we see today. They were massive, short-lived, and composed entirely of hydrogen and helium, the only elements that existed before heavier elements were forged in later generations of stars. If ultra-faint dwarfs truly are relics from this early era, then their chemical composition could reveal whether they once contained population 3 stars. Finding direct evidence of these first stars would be one of the greatest discoveries in astrophysics, shedding light on how the first elements in the universe were created and how the cosmos evolved from a sea of hydrogen into the rich, complex structures we see today. And yet, despite all our efforts, we are still left with more questions than answers. Do ultra-faint dwarfs represent a hidden chapter of cosmic history that we have yet to uncover? Are they the missing link between the early universe and the galaxies we see today? Or are they something entirely different, something that challenges everything we think we know about how the universe works? As telescopes grow more powerful and our ability to detect faint objects improves, we may soon find ourselves on the verge of answering these questions. But for now, ultra-faint dwarfs remain one of the greatest space mysteries of our time, a riddle written across the vast darkness of the cosmos, waiting to be solved. The search for answers continues, but every new discovery about ultra-faint dwarf galaxies only deepens the mystery. If these galaxies are truly ancient, then they hold secrets from the early universe, secrets that could completely change how we think about cosmic evolution. The problem is, they are incredibly difficult to study. Unlike massive galaxies that shine brightly with billions of stars, ultra-faint dwarfs are barely visible, their light so dim that they blend into the background of space. Even when we do detect them, learning about their structure and composition is a challenge. Most of the time, astronomers can only observe a handful of stars within these galaxies, making it nearly impossible to determine their full history. But there are ways to extract information, and one of the most important tools scientists use is spectroscopy, the study of how light interacts with matter. By analyzing the light coming from stars in an ultra-faint dwarf, astronomers can determine what elements those stars are made of. This is crucial because different generations of stars produce different chemical signatures. If an ultra-faint dwarf contains only the lightest elements, hydrogen and helium, it could mean that the galaxy is nearly as old as the universe itself. But if we find traces of heavier elements like carbon or iron, it suggests that the galaxy has gone through multiple generations of star formation, creating new elements over time. What's fascinating is that many ultra-faint dwarfs seem to have extremely low levels of heavy elements, far lower than what we see in larger galaxies. This could mean one of two things. Either these galaxies formed so early that they never had a chance to produce heavy elements, or something prevented them from forming new stars for billions of years. If it's the latter, then what could have halted star formation in these galaxies? One possibility is that after their first generation of stars exploded in massive supernovae, the force of those explosions was so powerful that it expelled all the gas from the galaxy, preventing new stars from forming. In a normal galaxy, gravity would pull that gas back in over time, allowing new stars to form. But ultra-faint dwarfs have such weak gravity that once the gas is gone, it never comes back. This raises an even deeper question. If these galaxies stopped forming stars billions of years ago, then why do they still exist? Most galaxies grow and evolve over time, merging with others and becoming part of larger structures. Yet ultra-faint dwarfs seem to have remained untouched, as if they've been frozen in time. One explanation is that they are protected by something we can't see, something that prevents them from being torn apart or absorbed into larger galaxies. This brings us back to dark matter. Many scientists believe that ultra-faint dwarfs are held together almost entirely by dark matter, making them some of the most dark matter-dominated galaxies in the universe. In other words, these galaxies might be made of more invisible matter than visible matter, which could explain why they've survived for so long despite their small size. If this is true, then ultra-faint dwarfs could be the perfect laboratory for studying dark matter. Since they contain so little regular matter, any unusual gravitational effects we see in these galaxies are likely caused by dark matter itself. This makes them an invaluable tool for testing different theories about what dark matter actually is. One of the biggest mysteries in physics today is whether dark matter interacts with itself. Most models assume that dark matter is cold, meaning it doesn't interact much with anything, including other dark matter particles. But some alternative theories suggest that dark matter might have self-interactions, meaning that dark matter particles could collide, scatter, or even form structures of their own. If ultra-faint dwarfs are full of dark matter, then studying their shape, movement, and density could tell us whether dark matter behaves the way we expect, or if it has unexpected properties that challenge our current understanding. There's also the possibility that ultra-faint dwarfs could be home to an entirely different kind of matter, something beyond what we currently recognize. Some physicists have speculated that these galaxies could contain primordial black holes, tiny black holes that formed in the first moments after the Big Bang. If true, then ultra-faint dwarfs might not just be a mystery about galaxies. They could be a window into the very birth of the universe itself. But the biggest mystery of all remains unsolved. If ultra-faint dwarfs are so old and so small, then why do they still exist in our modern universe? Shouldn't they have been destroyed or merged into larger galaxies long ago? And if they are truly relics from the early universe, how many more of them are still out there, waiting to be found? With new telescopes like the James Webb Space Telescope and upcoming surveys designed to map faint objects in the night sky, we may be on the verge of uncovering even more ultra-faint dwarfs. And if we do, they could hold the key to answering some of the biggest questions in astrophysics. Questions about dark matter, galaxy formation, and even the origins of the cosmos itself. But for now, the mystery remains. Ultra-faint dwarf galaxies are some of the strangest objects in the universe, hiding secrets that could change everything we know about space. The more we study them, the more we realize how little we understand. And perhaps that's the greatest mystery of all. Ultra-faint dwarf galaxies might be the key to unlocking some of the deepest mysteries of the universe. But the more we study them, the more questions arise. One of the biggest puzzles is how they formed in the first place. Most galaxies we observe today are thought to have started out as dense regions of gas in the early universe, where gravity pulled matter together until stars were born. However, ultra-faint dwarfs don't fit neatly into this model. Their incredibly low number of stars suggests that something prevented them from growing the way other galaxies did. Some researchers believe they may have formed in a unique environment, where the early conditions of the universe were vastly different from what we expect. Others think they might be remnants of much larger galaxies that were stripped down over billions of years, leaving behind only a faint core. If ultra-faint dwarfs really are ancient survivors, then they could contain some of the oldest stars in the universe. Studying these stars might reveal clues about the first moments after the Big Bang, a time when the universe was filled with raw, unprocessed matter. The oldest stars are expected to be made almost entirely of hydrogen and helium, since heavier elements only formed later through nuclear fusion inside stars. Astronomers have found that many stars and ultra-faint dwarfs do, in fact, have extremely low amounts of heavy elements. This suggests they belong to the very first generations of stars, meaning these galaxies might be some of the oldest structures in existence. But if that's the case, why do they look so different from other ancient galaxies? Most old galaxies have gone through cycles of star formation, producing new generations of stars over billions of years. Yet ultra-faint dwarfs seem to have been stuck in time, as if something halted their development early on. One possible explanation is cosmic reionization, a mysterious event that occurred when the universe was less than 1 billion years old. During this period, high-energy radiation from the first stars and galaxies stripped electrons from atoms, creating a sea of ionized gas. This event drastically changed the way galaxies formed, making it harder for small galaxies to hold on to their gas. Ultra-faint dwarfs might have been some of the hardest-hit victims of reionization. If they were already small to begin with, the intense radiation could have swept away their remaining gas, stopping star formation entirely. This would explain why they contain so few stars today, because they were essentially frozen in time billions of years ago. But there's another, even stranger possibility. Some researchers have suggested that ultra-faint dwarfs might not be normal galaxies at all. Instead, they could be something completely different, structures that formed in a way we don't yet understand. One radical idea is that they could be made of sterile neutrinos, a hypothetical form of dark matter that doesn't interact with regular matter in the usual way. If sterile neutrinos exist, they might explain why ultra-faint dwarfs seem so dominated by dark matter. Unlike regular galaxies, which have a balance of stars, gas, and dark matter, ultra-faint dwarfs appear to be almost entirely dark matter, with only a tiny fraction of visible stars. If their formation was driven by an unknown type of dark matter, it would challenge everything we thought we knew about how galaxies form. There's also the question of why ultra-faint dwarfs are still around today. If they are some of the oldest structures in the universe, shouldn't they have been destroyed by now? Many scientists expected that these small galaxies would have been absorbed by larger ones, yet somehow, they've survived for billions of years. One theory is that they exist in a kind of dark matter bubble, a protective shield created by their enormous dark matter content. If these galaxies are held together almost entirely by dark matter, then even as larger galaxies pull on them, they might resist being torn apart. This would mean that ultra-faint dwarfs are some of the strongest surviving remnants of the early universe, preserved by forces we still don't fully understand. But the biggest mystery of all might be how many more of them are still out there. The ones we've found so far are just the tip of the iceberg, and many astronomers believe that hundreds, if not thousands, of ultra-faint dwarfs remain undiscovered. Because they are so dim, they are nearly invisible to most telescopes, blending into the background of space. New surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to uncover many more of these galaxies in the coming years. And with each new discovery, we may get closer to answering the question of what these strange objects really are. Are they relics of the first galaxies, frozen in time for billions of years? Are they hidden laboratories for studying dark matter? Or are they something even stranger, evidence of a completely new kind of cosmic structure? For now, the mystery remains unsolved. But one thing is certain, ultra-faint dwarf galaxies are unlike anything else in the universe. They challenge our understanding of how galaxies form, what dark matter is, and how the universe evolved over billions of years. And the more we study them, the more we realize that we've only scratched the surface of one of the greatest cosmic mysteries of all time. Ultra-faint dwarf galaxies may hold secrets about the universe's infancy, but unlocking those secrets requires overcoming massive observational challenges. These galaxies are so dim that they barely register on even the most advanced telescopes. Unlike bright galaxies, which shine with billions of stars, ultra-faint dwarfs contain only a few thousand to a few 100,000 stars, making them among the least luminous galaxies ever discovered. The reason they are so faint is still a mystery. One possibility is that they formed in environments with very little gas, preventing them from producing many stars. Another idea is that they were once normal dwarf galaxies but lost most of their stars due to gravitational interactions with larger galaxies. But there's another possibility, one that could completely change how we understand galaxy formation. Some astronomers suspect that ultra-faint dwarfs might be failed galaxies, structures that tried to form like regular galaxies but were somehow stopped before they could grow. This could have happened if the dark matter halos that formed them were too weak to hold on to gas, or if an unknown cosmic event disrupted their development billions of years ago. To find more of these strange galaxies, astronomers have been searching the sky using deep sky surveys. The Sloan Digital Sky Survey (SDSS) was one of the first to reveal just how common ultra-faint dwarfs might be. Since then, other surveys, like the Dark Energy Survey (DES), have continued to uncover more of these ghostly galaxies, scattered like cosmic fossils throughout the universe. One of the most intriguing aspects of ultra-faint dwarfs is their motion. Unlike regular galaxies, which follow predictable paths based on gravity, these galaxies move in ways that don't always make sense. Some appear to orbit the Milky Way in unusual patterns, leading scientists to question whether an unknown force is at play. A major theory suggests that ultra-faint dwarfs might be key to understanding dark matter, the invisible substance that makes up most of the universe's mass. If dark matter behaves differently in these galaxies, it could mean that our current models of physics are incomplete. Some studies suggest that ultra-faint dwarfs have much more dark matter than expected, meaning they could be almost entirely made of it. This is where things get even weirder. If ultra-faint dwarfs are mostly dark matter, then studying them could give us the best chance at proving what dark matter really is. Some theories propose that dark matter is made of weakly interacting massive particles, WIMPs, while others suggest exotic particles like axions or sterile neutrinos. If we could analyze how dark matter interacts within these galaxies, we might finally be able to determine what it is. But here's the problem: dark matter doesn't emit light, making it nearly impossible to detect directly. The only way to study it is by looking at how it affects normal matter, like the tiny number of stars and ultra-faint dwarfs. This means that every newly discovered ultra-faint dwarf could bring us closer to solving the greatest mystery in modern astrophysics. The discoveries so far have already been groundbreaking. Some ultra-faint dwarfs seem to have no dark matter at all, contradicting the idea that dark matter is essential for galaxy formation. Others contain stars that are billions of years older than expected, suggesting they formed in the very first moments after the Big Bang. The implications of these findings are staggering. If ultra-faint dwarfs don't follow the same rules as other galaxies, then everything we thought we knew about galaxy formation might need to be rewritten. They could be evidence of an entirely new type of structure in the universe, something that formed under completely different conditions than anything we've ever seen before. And the strangest part? We might have only scratched the surface of this mystery. With new telescopes like the James Webb Space Telescope and the Vera C. Rubin Observatory coming online, we are on the verge of a revolution in our understanding of ultra-faint dwarfs. These observatories will allow us to see deeper into space than ever before, revealing more of these hidden galaxies and possibly answering the question of how they came to exist. But what if the answer is something we never expected? What if ultra-faint dwarfs aren't just ancient relics or dark matter laboratories, but something else entirely, evidence of an unknown force shaping the cosmos? Some scientists have even speculated that these galaxies could be influenced by new physics beyond our current understanding, hinting at deeper layers of reality we have yet to uncover. For now, the mystery of ultra-faint dwarf galaxies remains unsolved. But one thing is certain: these tiny, almost invisible galaxies may hold the key to answering some of the biggest questions about the universe. And as we continue to study them, we may find that the truth is even stranger than we ever imagined. Ultra-faint dwarf galaxies challenge our entire understanding of how galaxies form and evolve. They exist in a strange limbo between being legitimate galaxies and mere clusters of stars barely held together by gravity. The more we study them, the more they defy our expectations. If they truly are some of the first galaxies to ever form, then they are direct windows into the conditions of the early universe. If they are instead stripped-down remnants of larger galaxies, then they could tell us something new about the violent interactions between galaxies over cosmic time. One of the biggest questions astronomers face is whether ultra-faint dwarf galaxies are simply extreme versions of normal galaxies, or if they represent an entirely different class of objects. Traditional galaxy formation models suggest that all galaxies start out as small clumps of gas and dark matter that gradually merge and grow over billions of years. However, ultra-faint dwarfs seem to have remained in their tiny, undeveloped states for almost the entire history of the universe. This raises a fundamental question: what prevented them from evolving? Was it a lack of material to form stars? Was it an external force like cosmic reionization that stripped them of their potential? Or could it be that they formed in a completely different way from all other galaxies, meaning our theories of galaxy formation are incomplete? Recent studies have suggested that some ultra-faint dwarfs might be composed of a different kind of dark matter than what we typically assume. Most cosmological models assume dark matter is cold, meaning it moves slowly in clumps together, helping galaxies form. But if ultra-faint dwarfs are made of warm, or self-interacting dark matter, that would imply a completely new type of physics at play. This could have major consequences for our understanding of the universe. If dark matter interacts with itself in some way, then it might not just be an invisible backdrop to the cosmos. It could be actively shaping galaxies in ways we never predicted. And ultra-faint dwarfs, being so dominated by dark matter, could be the best places to test these theories. But the strangeness of ultra-faint dwarfs doesn't stop there. Some of these galaxies don't seem to be orbiting the Milky Way in a random pattern, as we would expect if they were simply captured by its gravity. Instead, they appear to be arranged in a vast, thin plane, a highly unlikely configuration if they were simply moving through space naturally. This odd arrangement has led some scientists to propose radical explanations. One idea is that these galaxies weren't formed the usual way at all, but instead are the remnants of a much larger structure that was torn apart. Another possibility is that they are following a hidden pattern dictated by dark matter itself, suggesting that dark matter might not be as invisible and featureless as we once thought. There's also the question of why ultra-faint dwarfs are so incredibly stable despite their low mass. Normally, small galaxies are expected to be torn apart by gravitational interactions with larger ones. Yet ultra-faint dwarfs have somehow survived for billions of years. This has led to speculation that they are held together by something beyond normal gravity, possibly even an unknown force related to dark matter. Some researchers have even suggested that ultra-faint dwarf galaxies might be evidence of a long-theorized concept known as fuzzy dark matter. In this model, dark matter isn't made of individual particles, but rather of wave-like structures that behave in strange, quantum mechanical ways. If this is the case, then ultra-faint dwarfs could be cosmic laboratories for testing one of the most exotic ideas in modern physics. No matter what the true nature of ultra-faint dwarf galaxies turns out to be, one thing is certain: they are rewriting the rules of astronomy. Every new discovery about them seems to challenge our previous assumptions about galaxy formation, dark matter, and the structure of the universe itself. And the biggest question remains: just how many more of them are out there? Given how difficult they are to detect, the ultra-faint dwarfs we've found so far may be just the tip of the iceberg. If thousands more of these hidden galaxies exist, they could completely reshape our understanding of the cosmos. With upcoming telescope missions poised to reveal even fainter objects than ever before, we are on the brink of discovering just how deep this mystery goes. And as we continue to uncover more ultra-faint dwarfs, we may find that the truth about these ghostly galaxies is even stranger than we ever imagined. The more astronomers study ultra-faint dwarf galaxies, the clearer it becomes that they don't fit neatly into any existing category. They aren't just small galaxies, and they aren't just failed galaxies either. They are something else, something that may redefine how we understand the universe. One of the most puzzling aspects of these galaxies is their extreme lack of stars. If a typical galaxy has billions or even trillions of stars, an ultra-faint dwarf might have only a few thousand. This is incredibly strange because, according to our best models of galaxy formation, dark matter should attract enough gas to form a much larger number of stars. But in these galaxies, something has prevented that from happening. One possible explanation is cosmic reionization. This event, which happened a few 100 million years after the Big Bang, was when the first stars and galaxies began emitting powerful radiation that stripped electrons from atoms across the universe. This process could have heated the gas in small galaxies, making it impossible for them to hold onto enough material to form new stars. If this is true, then ultra-faint dwarfs might be some of the oldest surviving structures in the universe, frozen in time from an era when galaxies were just beginning to form. But there's another mystery. Some ultra-faint dwarfs appear to have formed stars long after reionization should have stopped them. This suggests that either they somehow managed to hold on to their gas despite the harsh environment of the early universe, or that something else, something unknown, allowed them to form stars in a way we don't yet understand. Another question astronomers are trying to answer is whether ultra-faint dwarfs are truly independent galaxies or if they are simply remnants of larger galaxies that were torn apart. The key to this lies in their motion. If they were once part of bigger galaxies, we would expect their stars to be moving in specific patterns, as if they were the leftovers of a shredded system. However, observations suggest that many of these galaxies have their own unique orbits, as if they have been isolated for billions of years. And then there's the dark matter problem. Most galaxies contain dark matter, but ultra-faint dwarfs seem to have an extreme amount of it. In some cases, they appear to be over 99% dark matter, with only a tiny fraction of their mass made up of normal stars and gas. This is completely different from large galaxies like the Milky Way, which contain a much more balanced mix of dark and normal matter. Why would ultra-faint dwarfs be so dominated by dark matter? One theory is that these galaxies formed in regions of space where dark matter was unusually dense, meaning that even though they never gathered much normal matter, they still had enough gravity to survive for billions of years. Another idea is that ultra-faint dwarfs might be fossil galaxies, left over from the earliest era of galaxy formation, when dark matter played a much more dominant role in shaping the cosmos. But there's an even more bizarre possibility. Some researchers believe that ultra-faint dwarfs could be revealing a fundamental flaw in our understanding of gravity itself. According to standard physics, galaxies should behave in predictable ways based on their mass and dark matter content. But some ultra-faint dwarfs don't follow these rules. Their stars move in ways that suggest gravity is acting differently within them. This has led to speculation that dark matter might not exist in the way we think it does, or that an entirely new law of physics is at play. One alternative theory is called MOND, modified Newtonian dynamics, which proposes that gravity works differently at extremely low densities. If ultra-faint dwarfs are behaving in ways that don't match standard gravity models, they might be the best evidence yet that our entire understanding of the universe needs to be revised. And the mysteries keep piling up. Some ultra-faint dwarfs appear to be arranged in strange, ordered structures that can't be explained by random motion alone. They seem to form thin planes or synchronized orbits that suggest some unknown force is influencing their movement. This has led to speculation that dark matter might not be an invisible, uniform substance, but something far stranger, perhaps a hidden structure woven throughout the universe that shapes galaxies in ways we can't yet see. As telescopes continue to improve, we are beginning to detect even fainter and more distant dwarf galaxies. Some of these discoveries might hold the key to understanding what ultra-faint dwarfs really are. Are they the earliest galaxies that ever formed, still untouched by billions of years of evolution? Are they the remnants of a violent past, stripped down to their bare essentials by gravitational forces? Or are they something even stranger, evidence of hidden physics that we have yet to discover? One thing is certain. Ultra-faint dwarf galaxies are among the most mysterious objects in the universe. They challenge everything we thought we knew about galaxy formation, dark matter, and the fundamental laws of physics. Each new discovery about them brings more questions than answers, and as our ability to study them improves, we may find that the truth is even stranger than we ever imagined. The search for answers continues, and with every passing year, we are getting closer to uncovering the true nature of these cosmic ghosts. But until then, ultra-faint dwarf galaxies remain one of the greatest unsolved mysteries of the universe. A mystery that may change everything we thought we knew about space, time, and reality itself. The deeper we dive into the mystery of ultra-faint dwarf galaxies, the clearer it becomes that they may hold the key to solving some of the biggest puzzles in astrophysics. These galaxies are like time capsules, preserving conditions that existed when the universe was young. Their strange properties continue to defy expectations, forcing scientists to question everything from the role of dark matter to the basic rules of how galaxies evolve. One of the most baffling things about ultra-faint dwarfs is their sheer stability. According to conventional models of galaxy formation, small galaxies should be easily torn apart by interactions with larger galaxies. Yet these tiny, fragile-looking structures have somehow persisted for billions of years. If they truly are among the first galaxies to form, then they have survived all the chaos of the universe's evolution, from violent galaxy mergers to the constant pull of gravitational forces. But how? Some researchers believe that ultra-faint dwarfs are protected by an unusually strong dark matter halo. In most galaxies, dark matter is thought to form a loose cloud around the visible matter, providing enough extra gravity to hold everything together. But in ultra-faint dwarfs, dark matter seems to dominate almost completely. In some cases, for every single atom of normal matter in the galaxy, there might be thousands or even millions of times more dark matter. This overwhelming presence of dark matter could be what keeps these galaxies intact despite their incredibly low star count. But even this explanation has problems. If dark matter halos were this powerful, then we should see many more ultra-faint dwarfs in the universe than we do. Some scientists believe that we are only seeing the tip of the iceberg, that thousands or even millions of ultra-faint dwarfs are still out there, too dim to detect with current technology. Others think that something else is at play, possibly an unknown physical process that stabilizes these galaxies in ways we don't yet understand. And then there's the issue of missing dark matter. While most ultra-faint dwarfs appear to be dominated by dark matter, a few have been found that seem to contain almost none at all. This is a huge contradiction. If dark matter is necessary for galaxy formation, then how can a galaxy exist without it? Some astronomers speculate that these dark matter-free galaxies may have formed in an unusual way, perhaps through rare cosmic interactions that stripped them of their dark matter early in their history. Others believe that these galaxies could be proof that dark matter isn't a single, uniform substance but rather a collection of different unknown particles with varying properties. These strange galaxies also challenge the standard idea that all galaxies form by accumulating gas and gradually building up stars. Instead, ultra-faint dwarfs suggest that some galaxies may have formed in an entirely different way, perhaps through interactions with dark matter structures we can't see. If true, this would mean that galaxy formation is a much more diverse and complex process than previously thought. Ultra-faint dwarfs also provide an unexpected link to one of the biggest mysteries in modern physics: the nature of dark matter itself. Most of what we know about dark matter comes from observing its gravitational effects on galaxies. But because ultra-faint dwarfs have such an extreme ratio of dark matter to normal matter, they act as perfect natural laboratories for testing different dark matter theories. One of the leading ideas is that dark matter isn't completely passive but instead interacts with itself in some way. If this is true, then ultra-faint dwarfs could be the best place to observe these interactions in action. Some scientists think that by closely studying how stars move within these galaxies, we might be able to detect signs that dark matter has subtle, hidden forces acting upon it. If proven, this would be one of the biggest discoveries in physics, completely changing how we understand the universe. There's also the possibility that dark matter isn't even made of particles at all. Some theories propose that dark matter is actually a strange quantum field that behaves more like waves than particles. In this model, ultra-faint dwarfs might be shaped not just by gravity but by complex quantum effects that we haven't even begun to understand. If true, this would be a groundbreaking discovery, revealing an entirely new aspect of physics that could rewrite our understanding of the cosmos. Another mind-bending idea is that ultra-faint dwarf galaxies might be evidence of extra dimensions. Some physicists believe that dark matter could be leaking in from a hidden dimension that we can't see. If ultra-faint dwarfs are behaving strangely because they are interacting with something beyond our observable universe, then they could be the first real evidence that extra dimensions exist. All of these possibilities highlight just how little we truly understand about the universe. Ultra-faint dwarf galaxies seem simple at first glance, just small, dim clusters of stars. But the more we study them, the more they seem to defy our expectations. They might be the first galaxies ever formed, the missing pieces of the dark matter puzzle, or even the key to discovering new laws of physics that we've never imagined. And the search is far from over. New telescopes, like the upcoming James Webb Space Telescope and other next-generation observatories, are expected to reveal even more about these cosmic ghosts. As technology improves, we may finally be able to answer some of the biggest questions surrounding ultra-faint dwarfs. Are they truly the oldest galaxies in the universe? Do they hold the key to dark matter? And could they be evidence of entirely new physics that will change everything we know about the cosmos? One thing is for sure, ultra-faint dwarf galaxies aren't just a minor footnote in astronomy. They could be the missing puzzle pieces to some of the greatest cosmic mysteries. The more we uncover, the more we realize just how much we don't know. And perhaps, hidden among the vast darkness of space, these tiny, nearly invisible galaxies are quietly holding the answers to the biggest questions in the universe. Ultra-faint dwarf galaxies force us to rethink not just how galaxies form but also how the very fabric of the universe behaves. Their bizarre nature challenges our fundamental assumptions about dark matter, gravity, and even the way stars cluster together in the cosmos. If we want to understand the deeper mysteries of the universe, we have to confront the strange paradoxes these galaxies present. One of the most significant questions revolves around the role of dark matter in their structure. Traditional models suggest that galaxies form when gas collapses under its own gravity, eventually leading to the birth of stars. But ultra-faint dwarf galaxies seem to defy this rule. Many of them contain barely any gas at all, yet they still exist. This suggests that dark matter is playing a more active role in holding these galaxies together. If dark matter were just a passive gravitational force, then these galaxies should have dispersed long ago. Instead, they remain intact for billions of years, hinting at an unknown force at play. Some astronomers suspect that these galaxies are evidence of a cold dark matter model, where dark matter particles move very slowly and clump together in small halos. This could explain why ultra-faint dwarfs are so stable despite their low star count. But there's a problem. If cold dark matter behaves this way, then there should be far more ultra-faint dwarfs than we've detected. The fact that we don't see as many as expected suggests that something is missing from our understanding of dark matter. There's also the possibility that these galaxies are remnants of ancient cosmic structures. Some researchers believe that ultra-faint dwarfs may be the leftover building blocks of larger galaxies, fragments that never fully merged into the massive star systems we see today. If this is true, then studying them could provide a glimpse into what the earliest galaxies looked like before they evolved into their modern forms. But what if ultra-faint dwarfs are more than just relics? What if they represent an entirely different path of galaxy evolution? Some scientists speculate that these galaxies may have formed through interactions with exotic forms of dark matter that behave in ways we haven't yet discovered. If dark matter can clump together in unusual ways, then ultra-faint dwarfs might be a rare manifestation of this hidden process. This would mean that galaxy formation isn't a single, predictable process but rather a spectrum of different pathways influenced by dark matter's unknown properties. Another unsettling question is why some ultra-faint dwarfs seem to have almost no dark matter at all. If dark matter is necessary for galaxies to exist, then how can these galaxies survive without it? Some theories suggest that they may have originally contained dark matter but lost it due to powerful cosmic interactions. For example, a close encounter with a much larger galaxy could have stripped away the dark matter while leaving the stars behind. If this happened, it would mean that dark matter is more easily disturbed than previously thought, challenging the idea that it forms stable halos around galaxies. But there's another possibility, one that could shake the foundations of physics itself. What if dark matter isn't real? Some alternative theories propose that the strange behaviors we attribute to dark matter could actually be the result of modified gravity. In other words, the force of gravity itself may work differently on cosmic scales than we currently understand. If this is true, then ultra-faint dwarfs might not be anomalies at all. They might be proof that our entire model of how gravity works is incomplete. This idea, known as modified Newtonian dynamics, or MOND, suggests that gravity behaves differently in regions with extremely low densities, like ultra-faint dwarfs. If MOND is correct, then these galaxies could be the first real evidence that gravity doesn't follow the rules we expect at all scales. But proving this is difficult, and most astronomers still believe that dark matter is the more likely explanation. The mystery deepens when we consider the role of these galaxies in the larger structure of the universe. Cosmologists have long theorized that dark matter forms a vast cosmic web, with galaxies acting as nodes in this intricate network. If ultra-faint dwarfs truly contain vast amounts of dark matter, then they might serve as key points in this invisible structure, connecting larger galaxies in ways we don't yet understand. But if they lack dark matter, then they could be evidence that this cosmic web isn't as uniform as we thought. And what about the possibility that ultra-faint dwarfs are hiding even deeper secrets? Some scientists have proposed that these galaxies might be the best places to search for exotic physics beyond the standard model. For example, if dark matter particles occasionally decay into detectable signals, then ultra-faint dwarfs, being almost pure dark matter, could be the perfect laboratories for catching these rare events. If we find evidence of dark matter decay, It could be the breakthrough needed to finally prove what dark matter is actually made of. There's also the question of whether ultra-faint dwarfs could harbor signs of ancient activity that we haven't yet detected. Could they contain the remnants of the very first stars in the universe? Some of the oldest known stars have been found in these galaxies, suggesting that they could be among the longest living structures in the cosmos. If we can trace their histories, we might be able to uncover details about what the universe was like just a few 100 million years after the Big Bang. And then there's the strangest idea of all. What if ultra-faint dwarfs are linked to something beyond our current understanding of reality itself? Some speculative theories suggest that these galaxies could be interacting with unknown forces that exist outside of our observable universe. If our universe is part of a larger multiverse, then these galaxies might be showing us subtle signs of interactions with structures that exist in other dimensions. While this idea is purely theoretical, it raises the possibility that ultra-faint dwarfs could be windows into a much larger and more complex reality. Ultimately, the mystery of ultra-faint dwarf galaxies is a reminder of how little we truly know about the cosmos. These galaxies seem small and insignificant, yet they may hold answers to some of the biggest questions in astrophysics. Whether they reveal new details about dark matter, challenge our understanding of gravity, or even hint at the existence of hidden dimensions, one thing is certain: the more we study them, the more they force us to question everything we thought we knew about the universe. And the search is far from over. Future telescopes, like the Vera C. Rubin Observatory, will soon give us an even clearer view of these elusive galaxies. As we continue to explore the depths of space, we may finally unlock the secrets of ultra-faint dwarf galaxies, and in doing so, rewrite the very foundations of our understanding of the universe. Ultra-faint dwarf galaxies remain one of the most perplexing anomalies in astrophysics, challenging our understanding of galaxy formation, dark matter, and even the fundamental laws of physics. The more we study them, the more they defy conventional wisdom, raising questions that shake the very foundation of modern cosmology. Scientists have been attempting to piece together their origins, but every new discovery seems to deepen the mystery rather than solve it. One of the most confounding aspects of ultra-faint dwarfs is their extreme lack of visible matter. Traditional galaxy formation models suggest that gas collapses under gravity to form stars, but many ultra-faint dwarfs contain so little gas that this process seems impossible. So how did they form in the first place? Some theories suggest that they were once much larger, but intense gravitational interactions with larger galaxies stripped away their gas, leaving behind only the remnants we see today. Others propose that these galaxies never had much gas to begin with, and instead formed in an environment where gas was scarce. But if that's the case, then how did they manage to form any stars at all? This brings us to one of the biggest puzzles: the role of dark matter in their existence. Ultra-faint dwarfs appear to be dominated by dark matter, with their visible stars making up just a tiny fraction of their total mass. If dark matter is responsible for holding these galaxies together, then why do they behave so differently from larger galaxies, which also contain dark matter but form far more stars? The problem is that our current models predict that dark matter should clump together in specific ways, forming larger galaxies while leaving smaller ones to merge into bigger structures over time. But ultra-faint dwarfs seem to have remained isolated and unchanged for billions of years, suggesting that something is fundamentally wrong with our understanding of dark matter's behavior. One possible explanation is that dark matter itself isn't what we think it is. The standard model assumes that dark matter consists of weakly interacting massive particles, WIMPs, which exert gravitational influence but do not interact with normal matter in any other way. However, ultra-faint dwarfs could be evidence that dark matter is much more complex. Some scientists believe that dark matter may be self-interacting, meaning that dark matter particles could collide with each other, creating small-scale effects that explain the unusual properties of these galaxies. If this is true, then ultra-faint dwarfs might be the key to unlocking an entirely new understanding of dark matter. Another intriguing aspect of these galaxies is their incredibly old stars. Many of the stars found in ultra-faint dwarfs are some of the oldest in the universe, dating back nearly to the time of the Big Bang. This suggests that these galaxies may be relics from the early universe, frozen in time while other galaxies continue to evolve. If this is the case, then studying them could provide a glimpse into the earliest stages of galaxy formation, revealing details about how the first structures in the universe formed. But there's an even stranger possibility. What if ultra-faint dwarfs didn't form like normal galaxies at all? Some astronomers have suggested that they might be primordial galaxies, structures that formed directly from the initial conditions of the universe, without undergoing the same evolutionary processes as larger galaxies. If this is true, then these galaxies could be completely unique objects, separate from the standard framework of galaxy evolution. One particularly strange case is the ultra-faint dwarf galaxy Segue 1, which has been described as the least luminous galaxy known. With only a few hundred stars, Segue 1 is barely distinguishable from a star cluster, yet it behaves like a galaxy, with a gravitational pull that suggests it contains a massive amount of dark matter. The question is, why? Why would such a small collection of stars be surrounded by so much dark matter, and how has it remained stable for billions of years? Some researchers believe that Segue 1 could be a fossil galaxy, one of the first galaxies ever to form, surviving unchanged while the rest of the universe evolved around it. And then there's the possibility that these galaxies are revealing flaws in our understanding of gravity itself. The way ultra-faint dwarfs move doesn't always match the predictions of Newtonian physics, or even general relativity. If dark matter isn't the answer, then maybe our very concept of gravity needs to be re-examined. Some physicists have proposed alternative theories, such as modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at very low accelerations. If MOND is correct, then ultra-faint dwarfs could be the best evidence yet that our understanding of gravity is incomplete. These galaxies also raise questions about the large-scale structure of the universe. According to the standard model of cosmology, dark matter should be distributed in a cosmic web, with galaxies forming at the intersections of dark matter filaments. But if ultra-faint dwarfs contain enormous amounts of dark matter, then why do they exist in such isolated locations? Shouldn't they be clustered together more tightly? Some scientists speculate that these galaxies could be evidence of an unknown force shaping the distribution of dark matter in ways we don't yet understand. There's also the question of why some ultra-faint dwarfs appear to have little or no dark matter at all. If dark matter is essential for galaxy formation, then how can these galaxies exist without it? One idea is that they were once normal galaxies but lost their dark matter through interactions with larger galaxies. Another possibility is that these galaxies were never galaxies at all but rather star clusters that somehow gained enough mass to mimic the behavior of galaxies. But if that's the case, then why do they exhibit motions that suggest they contain hidden mass? Some astronomers have even suggested that ultra-faint dwarfs could be the remnants of ancient cosmic collisions. If two massive dark matter structures collided billions of years ago, the visible matter could have been stripped away, leaving behind only the scattered remnants we see today. If this theory is correct, then these galaxies could be evidence of massive, unseen cosmic events that shaped the universe in ways we've never imagined. And what if ultra-faint dwarfs are more than just cosmic leftovers? What if they're actually windows into a deeper reality? Some radical theories propose that these galaxies could be interacting with hidden dimensions or even parallel universes. If dark matter exists in extra dimensions, then ultra-faint dwarfs could be showing us glimpses of these hidden realms, manifesting as anomalies that don't fit into our standard models. While this idea is purely speculative, it raises profound questions about the nature of reality itself. Ultimately, ultra-faint dwarf galaxies challenge everything we think we know about the universe. They force us to confront deep, unresolved questions about dark matter, gravity, galaxy formation, and even the fundamental structure of space-time. Whether they turn out to be relics of the early universe, proof of exotic dark matter physics, or even hints at hidden dimensions, one thing is certain: these tiny galaxies hold some of the biggest mysteries in the cosmos. As telescopes like the Vera C. Rubin Observatory and the James Webb Space Telescope continue to study these enigmatic objects, we may soon find answers to some of these questions. But with every answer comes new mysteries, and ultra-faint dwarfs are unlikely to give up their secrets easily. The universe is far stranger than we ever imagined, and these tiny galaxies may be the key to unlocking some of its deepest and most profound mysteries. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.